In the vast, uncharted expanse of space, an invisible presence exists, silent yet all-consuming, devouring light itself. This enigmatic force is known as the cosmic void, a gargantuan, nearly empty region stretching across the universe in ways that defy our understanding. Astronomers have dubbed these immense voids cosmic deserts, vast areas of almost nothingness that can span billions of light years. These regions are not just empty spaces between galaxies. They are, in fact, fundamental structures woven into the very fabric of the cosmos, as crucial to the architecture of the universe as the galaxies themselves. Despite their importance, these voids remained largely unknown until relatively recently. It wasn't until 1981 that the first void was discovered, an astonishing revelation that overturned our prior assumptions about the distribution of matter across the cosmos. Until that point, scientists had assumed the universe to be relatively uniform, with galaxies scattered evenly across space, much like stars dispersed throughout the night sky. What they found, however, was far stranger, a universe not unlike Swiss cheese. Matter clusters in dense, concentrated regions, while vast bubbles of near-empty space, or cosmic voids, separate them. These voids, though they appear almost completely empty, contain some faint traces of matter, primarily hydrogen gas, scattered radiation, and the elusive dark energy that pervades all of space. However, compared to the bustling cosmic neighborhoods, where galaxies are densely packed into filaments and superclusters, these voids are places of rarefied emptiness. Within these voids, the density of matter drops to less than 20% of the cosmic average, making them true deserts of the cosmos. Yet, what makes these voids truly fascinating isn't simply the emptiness they represent, but their behavior. These voids are expanding at a rate faster than the rest of the universe, as though invisible hands are stretching the delicate web of space itself. This accelerated expansion provides scientists with vital clues about the nature of dark energy, the mysterious force that seems to drive the universe's expansion. The more we observe, the more we realize that these voids may hold the key to understanding the acceleration of cosmic growth. Even more puzzling, however, is the apparent motion of the voids themselves. Recent observations have revealed that galaxies on the edges of these voids seem to be moving away from the centers of the voids, as though fleeing an invisible, repulsive force. This phenomenon, known as void polarization, challenges our most fundamental models of cosmology, suggesting there may be aspects of physics that lie beyond our current comprehension. Among the most perplexing voids is one that lies uncomfortably close to us, the KBC void. Spanning nearly 1 billion light-years in size, this gargantuan bubble of emptiness sits directly in our cosmic neighborhood, with our own Milky Way galaxy placed bizarrely near its center. This positioning is so improbable that it calls into question the Copernican principle, the assumption that Earth, and by extension the Milky Way, occupies no special position in the universe. The existence of such a void so close to home raises profound questions about the randomness of cosmic structure and the nature of our place in the universe. This brings us to one of the most fundamental questions in cosmology. How did the universe begin? The prevailing theory, the Big Bang, proposes that approximately 13.8 billion years ago, all matter and energy in the universe existed in an incredibly hot and dense state, concentrated into a singularity. This singularity then underwent a rapid and violent expansion, known as the Big Bang, which gave rise to the universe as we know it today. It is important to note that the Big Bang wasn't an explosion in the conventional sense. Rather, it was a sudden expansion of space itself, an expansion that caused the universe to stretch, cooling as it did so. As the universe cooled, subatomic particles began to form, eventually combining to create the first atoms. Over billions of years, these atoms clumped together under the influence of gravity, eventually giving rise to the stars, galaxies, and large-scale structures we see scattered across the cosmos today. The Big Bang theory is supported by several compelling pieces of evidence. One of the most significant is the cosmic microwave background radiation, faint, ancient light that permeates all of space. This radiation, discovered in 1965, is the leftover heat from the Big Bang itself and provides a snapshot of the universe when it was just 380,000 years old. Another piece of evidence supporting the Big Bang is the observed abundance of light elements such as hydrogen, helium, and lithium. The proportions of these elements in the universe align perfectly with what we would expect if they had been created in the fiery aftermath of the Big Bang. Additionally, the observation of the universe's expansion, first noted by Edwin Hubble in the 1920s, provides further support for the Big Bang model. Distant galaxies appear to be moving away from us, with the speed of their recession increasing the farther they are from us. This observation suggests that the universe has been expanding ever since the Big Bang, a process that continues to this day. These observations collectively support the Big Bang theory, but many questions remain, particularly regarding the conditions that existed before the Big Bang. What happened prior to this event? The question of what came before the Big Bang is one of the most profound and elusive in cosmology. The theory of the Big Bang marks the beginning of our universe, but it offers no answers about what existed before this moment. Some hypotheses propose that the universe may have originated from a quantum vacuum or from a prior cycle of cosmic expansion and contraction. Others suggest that time itself began with the Big Bang, meaning that the very concept of before may be meaningless. One of the most intriguing ideas is the theory of eternal inflation, which proposes that our universe is just one of many bubbles in a vast, ever-expanding multiverse. Despite the tantalizing possibilities, our ability to investigate this pre-Big Bang era is limited. The cosmic horizon, the boundary beyond which we cannot observe, presents a formidable barrier. Moreover, the extreme conditions that prevailed at the very start of the Big Bang are beyond the reach of our current physical theories, which break down at such high energies and densities. Still, scientists are pushing the boundaries of what we know. By studying the cosmic microwave background radiation, researchers can glean insights into the universe's early moments. Particle accelerators, which recreate the extreme conditions of the early universe by smashing particles together at nearly the speed of light, offer another window into the universe's infancy. Additionally, theoretical physics and complex mathematical models help to refine our understanding of the earliest moments of cosmic history. One of the most influential theories to arise in recent years is that of cosmic inflation. This theory describes a period of rapid expansion that occurred just a fraction of a second after the Big Bang. During this time, the universe grew exponentially, expanding by a factor of at least 10 to the power of 26 in less than a billionth of a second. This brief but profound stretch helped to resolve several puzzles that the standard Big Bang theory could not explain. For example, it accounts for the uniformity of the universe in all directions, as well as its apparent flatness. Inflation also offers an explanation for the large-scale structure of the universe. During inflation, tiny quantum fluctuations, minute variations in the fabric of space-time, were stretched out to enormous scales. These fluctuations eventually became the seeds of the galaxies and galaxy clusters that we see today. In this way, cosmic inflation set the stage for the universe's ongoing expansion and the formation of the vast cosmic web that defines. The exploration of these early moments in the universe's history, while still in its infancy, continues to unlock the deepest mysteries of existence. What happened in the seconds, minutes, and years following the Big Bang remains one of the most profound questions in cosmology. But as our technology and understanding evolve, we may one day answer the most pressing question of all: how did it all begin? The origins and development of the universe have long been subjects of profound scientific inquiry, shaping our understanding of the cosmos and our place within it. While the precise causes of phenomena such as inflation remain the focus of ongoing research, the theories that have emerged offer valuable insights into the early universe and its subsequent evolution. Central to these discussions is the Big Bang theory, which remains the most widely accepted explanation for the universe's origin. According to this theory, the universe began as an infinitely small, hot, and dense point before rapidly expanding and cooling to form the structures we observe today. However, alternative models have also been proposed, each contributing to our evolving picture of cosmic history. One such alternative is the steady-state theory, which suggests that the universe has always existed in a state of equilibrium. In this view, the universe is continually expanding, but new matter is constantly being created to maintain a steady, unchanging density. Although this theory has been largely discounted due to overwhelming observational evidence supporting the Big Bang, it remains a testament to the early days of cosmological exploration, when scientists were grappling with the universe's vastness and origins. Another intriguing model is the cyclic model, which envisions the universe as undergoing an endless series of expansions and contractions. In this scenario, each cycle begins with a big bounce, rather than a singular Big Bang. The cyclic model aims to address some of the challenges posed by the Big Bang theory, particularly the nature of the initial singularity. It proposes that rather than having a single beginning, the universe is caught in a never-ending loop of birth, death, and rebirth. While this idea remains speculative, it continues to inspire debates on the ultimate fate of the universe. The erothic universe theory presents yet another fascinating perspective, suggesting that our universe emerged from the collision of two three-dimensional worlds within a higher dimensional space. This model attempts to explain certain phenomena, such as the uniformity of the cosmic microwave background radiation, without relying on the concept of cosmic inflation, a central feature of the standard Big Bang theory. While this idea is still largely theoretical, it offers a fresh way to think about the fundamental forces that shape our universe. In addition to these alternative models, concepts inspired by string theory, including the idea of a multiverse, have begun to capture the imagination of scientists and the public alike. String theory attempts to unify the fundamental forces of nature by positing that all particles are made of tiny, vibrating strings. Some versions of string theory suggest the existence of multiple dimensions beyond the familiar four, potentially housing parallel universes with entirely different physical laws. While these ideas are still very much in the realm of theoretical physics, they highlight the boundless curiosity that drives cosmological research. Despite the intrigue of alternative theories, the Big Bang theory remains the cornerstone of modern cosmology, providing the most coherent explanation for a wide range of observed phenomena. Yet, the quest for a deeper understanding of the universe's origins and evolution is far from over. As our tools and techniques improve, scientists continue to refine their models and push the boundaries of what we know about the cosmos. One of the key discoveries that has shaped our understanding of the universe's expansion is the role of dark energy. This mysterious force, which makes up roughly 68% of the total energy and matter in the universe, acts as a repulsive force that drives the universe's expansion at an accelerating rate. Unlike gravity, which pulls matter together, dark energy pushes everything apart. The first hints of dark energy came from observations of distant supernovae, which appeared dimmer than expected. This led to the realization that the expansion of the universe is speeding up rather than slowing down, as previously thought. Despite being one of the most dominant forces in the cosmos, the true nature of dark energy remains one of the greatest mysteries in modern physics. The implications of dark energy are profound. If its influence continues to dominate, the universe may undergo an endless expansion, stretching galaxies farther and farther apart. Eventually, this could lead to a cold, dark, and isolated cosmos where stars burn out and galaxies drift beyond the reach of one another. Although dark energy remains elusive, its discovery has sparked a flurry of theories and investigations, with scientists exploring everything from new forms of energy fields to the possibility that dark energy is an inherent property of space itself. Determining the age of the universe has also been a monumental endeavor, requiring the integration of numerous observational techniques and sophisticated models. One of the primary methods used to estimate the universe's age involves the measurement of the Hubble constant, which describes the rate at which galaxies are receding from us. By observing distant galaxies and calculating their speed, scientists can essentially trace the expansion of the universe backwards in time, arriving at an estimate for its age. Observations of galaxy rotation curves, for example, reveal that galaxies spin faster than they should based on the visible mass alone, suggesting that there is additional unseen matter influencing their motion. Gravitational lensing, where light from distant objects is bent by the gravity of massive structures, further supports the existence of dark matter. Studies of galaxy clusters also show that there is more mass present than can be accounted for by visible matter alone. The formation and distribution of large-scale structures in the universe, such as the cosmic web of galaxies, cannot be explained by ordinary matter alone, further suggesting that dark matter plays a crucial role in shaping the universe as we know it. As our understanding of the cosmos continues to evolve, the mysteries of dark energy, dark matter, and the fundamental nature of the universe remain at the forefront of scientific research. With each discovery, we inch closer to unraveling the secrets of the universe. Yet it remains an ever-expanding frontier, rich with questions yet to be answered. Furthermore, measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, have revealed startling insights about the universe. It turns out that ordinary visible matter, which forms everything we can directly observe, from stars and planets to dust and gas, makes up only about 5% of the total mass energy content of the universe. A far greater portion, approximately 27%, is dominated by dark matter, while the remaining 68% is attributed to an even more mysterious force, dark energy. This dark energy is believed to be the driving force behind the accelerated expansion of the universe, a phenomenon that remains one of the most profound puzzles in cosmology. Despite decades of intense research and numerous groundbreaking discoveries, the exact nature of dark matter remains elusive. Numerous leading theories have emerged over the years, proposing a range of exotic particles as potential candidates for dark matter. Among these are the weakly interacting massive particles, WIMPs, and axions, both of which could account for the gravitational effects attributed to dark matter. However, ongoing experiments in particle physics, astrophysics, and cosmology continue to search for answers, hoping to unlock one of the greatest mysteries in modern science. The first clues leading to the existence of dark matter were not the result of direct detection, but rather astronomical observations. In the 1930s, Swiss astronomer Fritz Zwicky made a groundbreaking discovery that would set the stage for future investigations into dark matter. While studying the Coma cluster of galaxies, Zwicky noticed something puzzling. The galaxies were moving much faster than expected, based on the visible matter alone. He proposed that an invisible form of matter must be exerting additional gravitational force, explaining the high velocities. This was the first suggestion that some unseen form of matter was influencing the motion of galaxies, yet the idea was largely ignored at the time. It wasn't until the 1970s that the dark matter hypothesis gained widespread attention. Researchers Vera Rubin and Kent Ford made a series of remarkable observations that provided compelling evidence for dark matter's existence. They found that stars located at the outer edges of galaxies were orbiting at speeds far too fast for the amount of visible mass in the galaxies to account for. This suggested the presence of a vast, unseen mass surrounding the galaxies, dark matter extending far beyond the visible limits of these cosmic structures. These findings marked a turning point in our understanding of the universe. The dark matter hypothesis proposes that a significant portion of the universe consists of matter that does not interact with light or other forms of electromagnetic radiation. This makes dark matter invisible to our most advanced telescopes, yet it still exerts a powerful gravitational influence on visible matter, affecting the behavior of galaxies and other large-scale cosmic structures. Since Rubin and Ford's discovery, a multitude of additional lines of evidence has supported the existence of dark matter, including the observed effects of gravitational lensing, the cosmic microwave background radiation, and complex computer simulations of galaxy formation. Despite all these indirect observations, however, the true nature of dark matter particles remains one of the most profound questions in modern cosmology. Scientists have devised a number of ingenious methods to attempt to detect dark matter, despite its elusive nature. One approach involves the use of large underground detectors filled with substances like liquid xenon or special crystals. These detectors are designed to capture the rare interactions between dark matter particles and normal matter, producing tiny flashes of light or heat that can be detected by sensitive instruments. In addition to direct detection efforts, scientists are also pursuing indirect detection methods. These involve searching for the byproducts of dark matter annihilation or decay. When dark matter particles collide, they may produce observable particles such as gamma rays or neutrinos, which can then be detected by telescopes and specialized detectors. These searches often focus on regions of space thought to harbor high concentrations of dark matter, such as the centers of galaxies. Particle accelerators, which smash particles together at incredibly high energies, offer another avenue for dark matter research. The hope is that these experiments might create dark matter particles under controlled laboratory conditions. If successful, such experiments could reveal important properties of dark matter, offering crucial insights into its composition and behavior. Gravitational lensing, too, provides a powerful tool for studying dark matter. As light from distant galaxies passes through regions of space filled with dark matter, the light's path is bent, creating distortions in the observed images. By carefully analyzing these distortions, researchers can map the distribution of dark matter across the universe. Dark matter is not only a key player in the overall structure of the universe, but it also plays a critical role in shaping the formation and evolution of galaxies. The gravitational influence of dark matter extends far beyond what we can observe with our telescopes, and it is believed to form the very backbone of cosmic structure. In the early universe, dark matter began to clump together under its own gravity, creating vast cosmic webs. These concentrations of dark matter acted as gravitational seeds, attracting normal matter and helping to form the first galaxies. As these proto-galaxies grew, dark matter continued to provide a gravitational scaffold, holding the galaxies together and influencing their rotation. The presence of dark matter is crucial in explaining why galaxies rotate much faster than would be possible based on their visible mass alone. Without dark matter, the outer regions of spiral galaxies would fly apart due to their rapid rotation. Instead, we observe that galaxies are surrounded by massive dark matter halos, extending far beyond their visible boundaries, providing the extra gravitational pull needed to keep stars in orbit. Dark matter also plays a major role in the large-scale distribution of galaxies across the universe. It forms cosmic structures such as galaxy clusters and vast filaments, guiding the placement of galaxies and shaping the cosmic landscape that we observe today. By studying these structures, scientists can map the distribution of dark matter and gain further insights into its role in cosmic evolution. Several intriguing candidates for dark matter particles have been proposed, each with unique properties that could explain this enigmatic substance. One leading contender is the weakly interacting massive particle, WIMP. These hypothetical particles would have substantial mass but would interact only weakly with normal matter, making them incredibly difficult to detect directly. Another promising candidate is the axion, a much lighter particle originally proposed to solve a problem in quantum chromodynamics. Axions could exist in vast numbers throughout the universe, potentially accounting for the observed effects of dark matter. Sterile neutrinos are yet another possibility. Unlike the known types of neutrinos, which rarely interact with matter, sterile neutrinos would be even more elusive. They could possess the right properties to serve as dark matter particles. Some researchers are also exploring more exotic possibilities, such as primordial black holes, which could have formed in the early universe, or self-interacting dark matter particles, which might explain certain galactic behaviors. As scientists continue to investigate these theoretical candidates using cutting-edge detectors and advanced observational techniques, the true nature of dark matter remains one of the most compelling and elusive mysteries in modern science. Dark matter's existence is indisputable in a sense. It is not only inferred from gravitational effects, but also shapes the very fabric of the universe itself. Yet, it remains an enigma, invisible and intangible, beyond the reach of current technologies. It does not emit, absorb, or reflect light, making it nearly impossible to detect directly. The only way dark matter interacts with regular matter appears to be through gravity. This gravitational influence is the reason we know dark matter exists. It explains the rotation of galaxies, the motion of galaxy clusters, and the bending of light in gravitational lensing. These observations reveal that there must be far more matter in the universe than can be accounted for by the visible, observable universe alone. However, beyond gravity, dark matter interacts very little with ordinary matter. It does not seem to collide with or stick to ordinary particles in any significant way, which means that it can pass through regular matter almost as though it doesn't exist at all. Enormous amounts of dark matter likely flow through the Earth every second, unnoticed by us. This elusive nature of dark matter presents a significant challenge to scientists trying to study it. To detect it, researchers are developing increasingly sensitive detectors that can capture the rare instances when dark matter particles interact with regular matter. As our understanding of dark matter grows, we may uncover new types of interactions between dark matter and regular matter, potentially revolutionizing our understanding of the universe. Another puzzle that has emerged is the missing satellite problem, which challenges our current understanding of dark matter and galaxy formation. According to current models of cold dark matter, large galaxies like our Milky Way should be surrounded by hundreds or even thousands of smaller satellite galaxies, each consisting of dark matter halos with varying amounts of visible matter, stars, and gas. However, such satellite galaxies have not been observed in the quantities predicted by these models, suggesting that there are still important aspects of dark matter's role in galaxy formation that remain to be understood. As science continues to probe the nature of dark matter, the question of how it shapes our universe and what it truly is remains one of the most profound challenges of our time. The universe has always held many secrets, some of which continue to elude even our most advanced scientific understanding. One of the most perplexing phenomena in modern astrophysics is the mysterious absence of satellite galaxies around our own Milky Way. Although theoretical models have predicted a much larger number of these smaller galaxies, what we observe is far less. To date, only a few dozen satellite galaxies have been identified around the Milky Way, leaving scientists to wrestle with a significant discrepancy between theory and observation. This mismatch between the expected and observed number of satellite galaxies has come to be known as the missing satellite problem, a conundrum that raises crucial questions about how galaxies form and, perhaps more fundamentally, about our understanding of dark matter. The missing satellite problem not only challenges the prevailing models of galaxy formation, but also suggests that there might be hidden truths about the fundamental forces governing the universe. Some researchers propose that there may be many more satellite galaxies out there, but they are simply too faint to be detected with the current technology at our disposal. These hypothetical galaxies, while undetectable by today's instruments, might still play a role in shaping the evolution of our cosmic neighborhood. Others contend that the missing satellite problem may reveal flaws in our current models of galaxy formation, specifically in how these models account for the behavior of dark matter on smaller scales. This ongoing debate has made the missing satellite problem one of the most active areas of research in both astrophysics and cosmology. Scientists are hard at work refining their observations, enhancing their theoretical models, and exploring new ideas to resolve this discrepancy. Each step closer to understanding the true number and nature of satellite galaxies brings us nearer to solving a greater mystery, one that could offer profound insights into the nature of dark matter and the forces that shape our universe. Dark matter, the elusive and invisible substance that makes up a staggering 85% of all matter in the universe, is intimately connected to the concept of missing mass. The term missing mass was first coined by astronomers when they noticed that galaxies were spinning far faster than would be expected based solely on the visible matter they contained. The unaccounted for gravitational effects led scientists to hypothesize that there must be an additional form of matter influencing these galaxies, but that it was somehow undetectable by conventional means. This invisible, non-luminous matter, now known as dark matter, interacts with normal matter solely through gravity, making it extraordinarily difficult to detect directly. Despite its ghostly nature, dark matter plays a crucial role in the formation and evolution of the cosmos. Its gravitational influence helps to bind galaxies together, affecting everything from the movement of stars to the very structure of the universe itself. Without dark matter, the cosmos as we know it would be a very different place. The study of dark matter remains one of the most pressing questions in modern astrophysics, as it holds the potential to unlock secrets about the very fabric of the universe. One of the primary challenges in studying dark matter is that it interacts with regular matter only through gravity and doesn't emit, absorb, or reflect light. As a result, dark matter cannot be observed directly. However, scientists have developed ingenious ways to probe its presence and properties. Large underground detectors, such as the xenon experiment in Italy, are designed to detect the rare interactions between dark matter particles and regular matter. These detectors use ultra-pure materials like xenon, and they are placed deep underground to shield them from cosmic rays and other forms of interference that could obscure the faint signals of dark matter. Similarly, experiments like the Large Underground Xenon LX experiment in South Dakota use liquid xenon in an attempt to detect the rare collisions between dark matter particles and xenon atoms. Meanwhile, researchers in Minnesota have turned to cryogenic crystals cooled to near absolute zero to detect the tiny amounts of energy deposited when dark matter particles collide with germanium and silicon detectors. These ultra-sensitive detectors may offer us a glimpse into the hidden world of dark matter. In addition to these underground experiments, scientists are exploring more unconventional methods to detect dark matter. One such approach involves the search for axions, hypothetical particles that could potentially explain both dark matter and certain aspects of nuclear physics. The Axion Dark Matter Experiment, ADMX, uses powerful magnets to search for these elusive particles. On a larger scale, space-based experiments such as the Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station are looking for indirect evidence of dark matter by measuring cosmic rays and antimatter in space. Despite these efforts, the true nature of dark matter remains an enigma. Theories abound as to what dark matter could be made of, with one of the most intriguing ideas suggesting that primordial black holes that formed in the earliest moments of the universe, could be responsible for the mysterious substance. Unlike stellar black holes, which form from the collapse of massive stars, primordial black holes would have formed due to extreme density fluctuations in the very early universe. These fluctuations, driven by quantum effects, could have caused matter to collapse into black holes almost immediately after the Big Bang. The appeal of this theory is that primordial black holes would be massive enough to explain the gravitational effects we observe, yet small and dark enough to have avoided detection by current observational methods. Moreover, this theory does not require the existence of new, undiscovered particles, which could make it an elegant solution to the dark matter mystery. However, recent observations have placed strict limits on the number of primordial black holes that could exist in certain mass ranges, making it less likely that these objects could account for all of the dark matter in the universe. While the primordial black hole hypothesis remains intriguing, it is just one of many competing theories, and scientists continue to investigate this possibility alongside other potential candidates. In addition to dark matter, another cosmic mystery that has reshaped our understanding of the universe is dark energy. Dark energy is the force responsible for the accelerating expansion of the universe, and like dark matter, it is invisible and difficult to study directly. Discovered unexpectedly in the late 1990s, dark energy was first identified when astronomers observed that distant supernovae, explosive events marking the death of massive stars, were fainter than expected. This led scientists to conclude that these supernovae were farther away than predicted, suggesting that the expansion of the universe was actually accelerating rather than slowing down as previously thought. The discovery of this acceleration was revolutionary. It pointed to the existence of an unknown energy source working against gravity on a cosmic scale. This unknown force was dubbed dark energy, and it has since become one of the central mysteries of modern cosmology. Dark energy is thought to make up about 68% of the total energy and matter in the universe. However, despite its pervasive presence, scientists still have very little idea what dark energy actually is or how it works. Unlike gravity, which pulls matter together, dark energy acts as a kind of cosmic repellent, pushing galaxies apart at an ever-increasing rate. As the universe expands, the amount of dark energy increases, creating more space between galaxies and galaxy clusters. This leads to a runaway effect, where the rate of expansion continues to accelerate over time. While we can observe the effects of dark energy, its true nature remains one of the greatest unsolved problems in modern physics. Scientists are racing to understand this mysterious force, and as our knowledge grows, we may come to understand not just dark energy, but also the ultimate fate of the universe itself. These mysteries, dark matter, dark energy, and the missing satellite problem, are just a few of the cosmic puzzles that scientists are working tirelessly to solve. As we continue to explore the farthest reaches of space and the deepest mysteries of the universe, our understanding of the forces that govern the cosmos will undoubtedly evolve, potentially reshaping our view of the universe's past, present, and future. With each new discovery, we move one step closer to unraveling the intricate tapestry of the cosmos and uncovering the secrets that lie hidden within the vast expanse of space. Dark energy is one of the most profound mysteries in modern cosmology, yet its influence on the universe's fate is irrefutable. The concept of dark energy fundamentally shapes the way we predict the ultimate destiny of the cosmos. It has the potential to determine whether the universe will continue to expand forever, driven by its own self-perpetuating force, or whether the vast stretches of space will eventually collapse back upon themselves in a dramatic reversal of expansion. Understanding dark energy is, therefore, not merely an academic exercise. It is crucial for answering one of the most fundamental questions of our existence: what will happen to the universe in the distant future? Despite its critical role in cosmic evolution, dark energy remains one of the most enigmatic aspects of contemporary physics. Over the years, numerous theories have been proposed to explain the behavior of this mysterious force, each attempting to untangle its puzzling effects on the fabric of space. Of these, the cosmological constant has emerged as the leading candidate. Initially proposed by Albert Einstein in 1917, this concept suggests that dark energy is an intrinsic property of space itself. According to this theory, space has a constant energy density that fills every corner of the universe, and as space itself expands, so too does the amount of dark energy within it. This self-replicating nature of dark energy drives the continued acceleration of the universe's expansion, with each new stretch of space contributing to its own enlargement. However, the cosmological constant is not the only theory on the table. Another prominent idea is quintessence, a theory that challenges the notion of dark energy as a static, unchanging force. Instead, quintessence proposes that dark energy is dynamic, a field that evolves over time and space, changing in strength and effect as the universe ages. This dynamic view of dark energy could potentially explain the varying rates at which the expansion of the universe has accelerated at different points in cosmic history. Unlike the cosmological constant, quintessence is not a fixed property of space, but a field whose characteristics can fluctuate, adding a layer of complexity to our understanding of cosmic expansion. Some researchers have even suggested that dark energy might not be a new form of energy at all, but a manifestation of how gravity behaves on vast scales. These modified gravity theories propose that the forces we observe as dark energy could, in fact, be explained by adjustments to our understanding of gravity at the largest distances. If gravity behaves differently in the farthest reaches of the cosmos than we currently understand, it could explain the observed acceleration in the universe's expansion without invoking an entirely new form of energy. As scientists continue to investigate dark energy, they employ a variety of sophisticated techniques to measure its effects on the universe. One of the most significant methods involves the observation of type 1a supernova, exploding stars that have a consistent peak brightness. By measuring how bright these supernovae appear from Earth, astronomers can calculate their distance and determine how quickly they are receding from us. This allows them to track the rate at which the universe is expanding, offering critical insights into how dark energy is influencing cosmic acceleration. The discovery of the accelerating expansion of the universe, a groundbreaking finding that earned the Nobel Prize in Physics in 2011, was made possible by this very technique. Another key observational tool in dark energy research is the cosmic microwave background, CMB radiation, which is the afterglow of the Big Bang. Tiny fluctuations in this ancient light provide a snapshot of the universe's early conditions, revealing how it evolved from a hot, dense state to the vast, expanding cosmos we observe today. By studying these fluctuations, scientists can infer the amount of dark energy present in the universe and how it has shaped the expansion of space since the beginning of time. Gravitational lensing, the bending of light by massive objects, is also a critical technique for understanding dark energy. As light from distant galaxies passes through intervening cosmic structures, it is distorted, revealing both the distribution of visible matter and elusive dark matter that permeates the universe. By mapping these distortions, scientists gain valuable insights into the structure and evolution of the cosmos, helping to refine models of how dark energy has influenced cosmic growth. Large-scale galaxy surveys provide additional data that helps astronomers track the movements of galaxies and detect patterns in the distribution of matter across the universe. These surveys enable scientists to observe subtle signatures of dark energy, revealing how its effects play out across cosmic distances and over long periods of time. By mapping millions of galaxies, scientists are better able to test competing theories of dark energy, refining our understanding of how it drives the expansion of the universe. In this context, the cosmological constant has become a cornerstone of our understanding of dark energy. In Einstein's equations of general relativity, the cosmological constant represents a constant energy density that fills all of space, a concept originally introduced by Einstein himself to explain a static universe. Although he abandoned the idea after the discovery that the universe is expanding, the cosmological constant has experienced a resurgence in modern cosmology. Today, it is closely associated with dark energy, as both concepts describe a form of energy that permeates space and exerts a negative pressure. This negative pressure counteracts the force of gravity, which is responsible for the observed acceleration in the expansion of the universe. While the cosmological constant offers a simple, elegant explanation for dark energy, its exact nature remains elusive. Despite decades of study, scientists still struggle to fully comprehend the properties of this mysterious force. Some believe that it might be linked to the concept of vacuum energy, a form of energy that is thought to be inherent in the fabric of empty space. If dark energy is indeed a manifestation of vacuum energy, it would have profound implications for our understanding of the universe and the laws of physics. In addition to these well-established theories, more speculative ideas continue to emerge. One possibility is that the accelerating expansion driven by dark energy will ultimately result in the big freeze or heat death of the universe. In this scenario, the universe will continue to expand at an ever-increasing rate, causing galaxies to drift further apart. Over billions of years, stars will exhaust their fuel, and the cosmos will grow cold and dark. Only remnants of stars, such as black holes, neutron stars, and burned-out stellar corpses will remain, casting a chilling shadow over the universe's future. Alternatively, dark energy might cause the expansion to reach such extreme levels that it will eventually tear the very fabric of the universe apart. This Big Rip scenario suggests that the force driving the expansion of the universe could grow stronger over time, ultimately overcoming the forces holding galaxies, solar systems, and even atoms together. If dark energy's strength increases in the future, the universe could undergo a catastrophic breakup at the most fundamental level, leading to the disintegration of all matter. The theory of quintessence offers an alternative to the cosmological constant, proposing that dark energy is not static but a dynamic field that evolves over time. Unlike the cosmological constant, which assumes a uniform energy density across the cosmos, quintessence allows for the possibility that dark energy's strength and distribution could change over cosmic history. This would resolve some of the fine-tuning problems associated with the cosmological constant and offer a more nuanced explanation for the acceleration of the universe's expansion. If quintessence proves to be the correct theory, the future of the universe could be far more complex than simple eternal expansion or catastrophic disintegration. Instead, periods of accelerated expansion could alternate with phases of deceleration or even oscillation in the expansion rate. As scientists continue to probe the mysteries of dark energy, they face challenges that stretch the limits of our current understanding of physics. This force, which seems to defy the very laws of nature, is pushing the boundaries of what we know about the universe. Its uniformity, its effect on space and time, and its apparent contradiction with the expectations of classical physics all point to a need for new theories and paradigms. As our understanding of dark energy deepens, we may not only gain insights into the fate of the cosmos, but also uncover new dimensions of the universe itself, changing forever our view of the cosmos and our place within it. When scientists attempt to calculate the amount of vacuum energy using quantum field theory, they encounter an astounding result that seems almost absurd. The theoretical value comes out to be vastly different from any observations, off by a factor of 10 to the power of 120. This enormous discrepancy highlights the profound limitations of our current understanding of quantum mechanics and general relativity. It draws attention to an alarming gap in our knowledge, urging scientists to push the boundaries of existing theories. As a result, dark energy has emerged as one of the most perplexing puzzles in modern cosmology, demanding new models that can reconcile the behavior of the very small, such as particles, with the very large, like galaxies and the universe itself. Dark energy's mysterious nature poses a cosmic challenge to the scientific community. However, its existence is supported by a variety of compelling observations, each providing essential clues that help reshape our understanding of the cosmos. Among the most powerful pieces of evidence is the study of Type 1a supernovae in distant galaxies. These stellar explosions act as cosmic standard candles, allowing astronomers to measure the rate at which the universe is expanding at different points in time. When scientists first observed these supernovae, they anticipated that the universe's expansion would be slowing down, a natural outcome of gravity's influence. However, the data revealed an unexpected twist. The universe's expansion is not slowing, it is accelerating. This acceleration implies the presence of a force pushing galaxies apart at ever-increasing speeds, a force that scientists have named dark energy. This discovery, made in the late 1990s, forever changed our understanding of the universe's fate, pointing to an unknown force acting against the pull of gravity. Another critical line of evidence supporting dark energy comes from the study of the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang. Detailed measurements of this ancient radiation provide a snapshot of the early universe, offering insights into its geometry, composition, and structure. The patterns observed in the CMB align with models of the universe that include dark energy. These patterns suggest that dark energy accounts for approximately 68% of the total energy content in the universe. This fraction is a staggering revelation, highlighting the profound influence of dark energy on the large-scale structure of the cosmos. The discovery of dark energy through the CMB and other measurements forces us to reconsider our models of the universe's development and future. Large-scale surveys of galaxies provide further evidence for the existence of dark energy. These surveys track the distribution of galaxies across vast expanses of space. The observed clustering of galaxies is consistent with predictions made by cosmological models that incorporate dark energy. Without dark energy, the way galaxies group together on enormous scales would be difficult to explain. Furthermore, gravitational lensing, an effect predicted by Einstein's theory of general relativity, adds another layer of evidence. Gravitational lensing occurs when light from distant galaxies is bent by the gravity of intervening objects. Observations of this bending help astronomers estimate the total amount of matter in the universe, indirectly supporting the need for dark energy to explain the universe's behavior. Together, these lines of evidence create a compelling case for the reality of dark energy, even as scientists continue to debate its fundamental nature. Despite the growing body of evidence supporting its existence, dark energy remains one of the most enigmatic concepts in modern physics. Scientists have proposed various hypotheses to explain its nature, but none have yet provided a complete answer. One idea suggests that dark energy is a fundamental property of space itself, an inherent characteristic of the fabric of the cosmos. This concept closely aligns with Albert Einstein's notion of the cosmological constant, which he introduced in 1917 to create a static model of the universe. According to this theory, as the universe expands, more space is created, and with it, more dark energy. This would naturally lead to the acceleration of cosmic expansion, as we observe today. If correct, this theory suggests that dark energy is woven into the very fabric of space-time, present everywhere, in every corner of the universe. This idea carries profound implications for the fate of the universe. If dark energy is indeed an intrinsic property of space, the universe will continue to expand indefinitely. Over vast timescales, this expansion would eventually lead to a scenario known as the Big Freeze. In this future, galaxies, stars, and even atoms would become increasingly distant and isolated as the universe grows colder and more diffuse. However, it is essential to note that this remains a hypothesis, and other explanations for dark energy are still being explored. Some scientists are investigating the possibility that our understanding of gravity is incomplete, and that dark energy may arise from modifications to our gravitational models. Others speculate about the existence of unknown fields or particles that could permeate space, exerting the effects we attribute to dark energy. These theories continue to drive much of the research into dark energy, and the true nature of this cosmic force remains one of the greatest open questions in modern science. The nature of black holes further challenges our understanding of the universe. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape. They form when massive stars collapse at the end of their life cycles. As a star runs out of fuel, it can no longer support its own weight, leading to a catastrophic implosion. The collapse forces all of the star's mass into an incredibly tiny space, creating a singularity, an infinitely dense point at the heart of the black hole. Around this singularity, a boundary forms called the event horizon. This marks the point of no return. Anything that crosses it is inexorably drawn into the black hole, never to escape. Black holes come in a variety of sizes, from stellar black holes, which form when individual stars collapse and can be several times more massive than our Sun, to supermassive black holes found at the centers of most galaxies. These supermassive giants can be millions, even billions of times more massive than the Sun. Over billions of years, supermassive black holes may grow by consuming nearby stars or by merging with other black holes. The study of these cosmic giants offers valuable insights into the nature of space-time and the fundamental forces that govern the universe. In addition to stellar and supermassive black holes, scientists have discovered evidence for a new class: intermediate mass black holes. These lie between the two other types, providing an important bridge in our understanding of black hole formation and growth. Whether stellar or supermassive, black holes continue to fascinate researchers, offering glimpses into the extreme realms of physics where gravity, time, and space behave in ways that challenge even our most advanced theories. At the event horizon, black holes exhibit strange and extreme phenomena. As an object approaches this boundary, it is subjected to intense gravitational forces. Time appears to slow down dramatically for a distant observer, while the object itself experiences violent stretching and compression. This phenomenon, known as spaghettification, occurs because the tidal forces near a black hole differ from one point to another. The gravitational pull is stronger at the object's nearer end, stretching it vertically while compressing it horizontally. The result is a disintegration of the object's structure as it is pulled apart into its fundamental components. Once an object crosses the event horizon, its fate becomes uncertain. Some theories suggest that information about the object is preserved on the surface of the event horizon, a hypothesis known as the holographic principle. Others argue that all information is lost, forever trapped within the black hole. This debate, the so-called black hole information paradox, is one of the most profound mysteries in modern physics. It pits the principles of quantum mechanics, which suggests that information cannot be destroyed, against general relativity, which describes the behavior of large-scale gravitational forces. Moreover, black holes are not static objects. They emit a faint form of radiation, known as Hawking radiation, named after physicist Stephen Hawking. This radiation arises from quantum effects near the event horizon and leads to the gradual evaporation of black holes over vast timescales. The discovery of Hawking radiation adds another layer of complexity to our understanding of black holes, suggesting that even these seemingly eternal cosmic objects are not invincible. As black holes slowly lose mass through Hawking radiation, they may eventually disappear, leaving behind only a faint trace in the fabric of the cosmos. In summary, both dark energy and black holes remain central to our quest for understanding the universe. While we have made significant strides in uncovering the evidence for dark energy, its true nature remains elusive. Similarly, black holes continue to challenge our understanding of space-time and the fundamental laws of physics. Together, these cosmic phenomena push the limits of scientific knowledge, demanding new theories and models to unlock the deepest secrets of the universe. As our observational tools improve and our theories evolve, the answers to these profound mysteries may finally emerge, reshaping our understanding of the cosmos in ways we can only begin to imagine. However, the story doesn't end there. In the 1970s, physicist Stephen Hawking introduced a groundbreaking idea that changed the way we think about black holes. He proposed that black holes might not be completely black after all. His suggestion? Black holes could emit a faint glowing radiation due to quantum effects near the event horizon. This mysterious emission, now known as Hawking radiation, has become one of the most discussed concepts in modern physics. According to Hawking, at the event horizon, the boundary beyond which nothing, not even light, can escape, a peculiar process occurs. In the vacuum of space, particle-antiparticle pairs constantly pop into existence, only to annihilate each other moments later. But near the intense gravitational field of a black hole, one of these particles may be drawn into the black hole while the other escapes, appearing as radiation. This phenomenon slowly depletes the black hole's mass and energy over incredibly long periods of time. The larger the black hole, the slower this process occurs, but for smaller black holes, it could eventually lead to their evaporation. While Hawking radiation has not been directly observed due to its incredibly faint nature, the theory represents a fascinating intersection between two of the most fundamental areas of physics, quantum mechanics and general relativity. If this theory is correct, it challenges the classical view that nothing can escape from a black hole. Instead, it suggests that information and energy can slowly leak out in a form entirely different from the way they originally entered. In addition to Hawking radiation, another concept related to black holes has captured the attention of physicists: gravitational waves. When black holes collide or merge, they send ripples through the fabric of space-time. These waves carry vital information about the black holes, information that would otherwise be trapped within them. This gives rise to an intriguing possibility that there may be a form of escape from these cosmic giants in the form of gravitational waves. The idea of Hawking radiation is rooted in quantum mechanics, which deals with the bizarre and counterintuitive behavior of particles on the smallest scales. In the quantum world, particles can appear and disappear spontaneously. But when these particles interact with the immense gravity of a black hole, one of them might fall in and the other might escape, leading to the radiation that depletes the black hole over time. This process is incredibly slow, especially for large black holes, but it offers a potential mechanism for their eventual disappearance. If this happens, it would have profound implications for one of the biggest puzzles in theoretical physics, the black hole information paradox. According to quantum theory, information cannot be destroyed, but black holes, with their ability to trap everything, including information, seem to defy this fundamental principle. Hawking's theory, if correct, could provide a resolution by suggesting that black holes slowly leak information through the Hawking radiation, though in a way vastly different from what we would expect. Another key piece of the black hole puzzle is the nature of supermassive black holes. These colossal objects, millions to billions of times the mass of our Sun, sit at the centers of most galaxies, including our own. Their formation remains one of the most puzzling topics in modern astrophysics. One leading theory posits that these supermassive black holes started as small seed black holes formed in the early universe. These seeds might have originated from the collapse of massive stars or from dense gas clouds. Over time, these black holes grew by absorbing matter and when merging with other black holes, especially during galactic collisions. Alternatively, supermassive black holes may have formed from the direct collapse of massive gas clouds in the early universe, producing black holes with masses of hundreds of thousands of times that of the Sun. This would have given them a substantial head start in their growth, as galaxies themselves began to form and evolve. As the universe aged, these black holes continued to grow, accumulating gas, dust, and even stars that ventured too close, making them some of the most powerful objects in the cosmos. The mergers of black holes themselves are among the most extraordinary events in the universe. As two black holes spiral toward each other, they create a gravitational dance that sends ripples through space-time, known as gravitational waves. In the final moments before their collision, these black holes move at nearly the speed of light. When they merge, a portion of their combined mass, often equivalent to several suns, converts into pure energy, released in a burst of gravitational waves. These waves carry more energy than all the light emitted by all the stars in the observable universe. The newly formed black hole, created from the merger of its predecessors, briefly wobbles and rings like a bell, sending out gravitational waves at specific frequencies. This ringing gradually fades as the black hole settles into a stable state. Meanwhile, a nearby gas or dust that gets caught in the gravitational chaos is heated to extreme temperatures, creating a flare of light visible to astronomers. These mergers not only offer stunning visual displays, but also provide a wealth of information for scientists. By detecting and analyzing the gravitational waves emitted during these events, physicists can test Einstein's theories and gain new insights into the nature of gravity, space-time, and the universe itself. Despite their invisibility, black holes are not beyond detection. Scientists have developed sophisticated methods to study them indirectly. One of the most effective techniques involves observing the behavior of stars and gas near a black hole. As matter falls toward a black hole, it forms an accretion disk, a swirling mass of superheated material. This disk emits powerful X-rays, which can be detected by space telescopes. Another critical approach involves the detection of gravitational waves. When massive objects like black holes collide, they generate ripples in space-time. Earth-based detectors such as the Laser Interferometer Gravitational Wave Observatory, LIGO, measure these minute distortions. By analyzing these waves, scientists can study black hole mergers in greater detail than ever before, opening up a new field of gravitational wave astronomy. Yet the question of what happens to matter and energy that falls into a black hole remains one of the most intriguing and perplexing mysteries in physics. According to Stephen Hawking's discovery, black holes emit Hawking radiation, which causes them to slowly evaporate over time. However, this radiation seems to be purely random and devoid of any information about the matter that fell into the black hole. This presents a paradox. If a black hole evaporates completely, taking all the information it has absorbed with it, this would violate the fundamental principles of quantum mechanics, which insist that information cannot be lost. This contradiction between the preservation of information in quantum mechanics and the apparent loss of information in black holes is known as the black hole information paradox. It has puzzled physicists for decades and remains one of the most active areas of research in theoretical physics. Possible resolutions to the paradox involve concepts like holography, firewalls, and even radical revisions to our understanding of space and time at the quantum level. Among the most thought-provoking ideas related to black holes is the possibility that our entire universe might exist inside a black hole. This idea, known as black hole cosmology, has fascinated scientists and cosmologists alike. The theory is based on the curious similarities between black holes and the early universe. Both involve incredibly dense concentrations of matter and energy at the singularity of a black hole and at the moment of the Big Bang. Furthermore, the expansion of our universe shares mathematical similarities with the properties of a black hole's event horizon. While this notion is tantalizing, it remains highly speculative. Our current understanding of the universe and the laws of physics does not provide concrete evidence to support or disprove this idea. Nonetheless, the concept of black hole cosmology remains a fascinating possibility, one that continues to spark the imagination of researchers. Finally, the idea of white holes, theoretical objects that are the opposite of black holes, has also captured the attention of physicists. While black holes pull everything in, including light, white holes would theoretically expel matter and energy. White holes emerge from the same equations of general relativity that describe black holes, and they represent an intriguing solution to these equations. Some theories suggest that white holes could be the other end of black holes, connected by a hypothetical structure known as a wormhole, or an Einstein-Rosen bridge. This idea, though still speculative, continues to be explored in the search for a deeper understanding of the universe and the potential for connections between distant parts of space-time. The study of black holes, with their many mysteries and paradoxes, continues to push the boundaries of human knowledge. Each discovery, each new theory, brings us closer to understanding the nature of these enigmatic objects and the fundamental workings of our universe. The journey is far from over, and as we continue to unravel the secrets of black holes, we may uncover truths about the very fabric of space-time itself. However, despite the fact that black holes have been indirectly observed and studied in detail, white holes remain purely theoretical. Their existence has not been confirmed by any empirical evidence in the observable universe, which makes them an elusive and fascinating concept within the field of theoretical physics. While black holes, mysterious objects from which nothing, not even light, can escape, are well documented and studied extensively, white holes remain largely speculative. Some physicists, however, question the very feasibility of their existence. They argue that white holes would be inherently unstable, their theoretical nature so fragile that they might not be able to exist for any meaningful length of time. This debate sheds light on the delicate balance within the fabric of space-time, illustrating how even the most intriguing cosmic phenomena must contend with the physical constraints of our universe. The relationship between black holes and white holes reflects the extreme conditions that define space-time. While black holes continue to be a subject of intense study, pushing the boundaries of our understanding of gravity, singularities, and the very nature of the universe, white holes remain a theoretical curiosity, an idea that stretches the imagination and challenges our understanding of the cosmos. Although scientists continue to probe the nature of black holes, the concept of white holes serves as a fascinating intellectual exercise, highlighting the many mysteries that still lie hidden beneath the surface of reality. Time itself is one of the most profound and enigmatic aspects of our universe. It is intricately woven into the fabric of reality, forming an essential dimension alongside the three spatial dimensions we experience daily. Time is the measure of change and the sequence of events, allowing us to differentiate between past, present, and future. Unlike space, which we can easily perceive and navigate, time has a peculiar quality. It flows in only one direction. This forward march of time is commonly referred to as the arrow of time, a term that encapsulates the seeming inevitability of the passage from past to future. But what drives this unidirectional flow? It is closely linked to a fundamental concept in physics known as entropy. Entropy is a measure of disorder within a system, and according to the second law of thermodynamics, the total entropy of an isolated system will always increase over time. As time progresses, systems naturally evolve towards greater disorder and greater spread. This constant and irreversible increase in entropy gives time its apparent direction. This concept can be illustrated in simple ways in our everyday lives. For example, if you crack an egg, you will never observe that egg spontaneously reassembling itself. The past remains fixed in our memories, while the future is uncertain and unknown. These phenomena are all manifestations of the arrow of time, with entropy driving the directionality of time itself. At the quantum level, the situation becomes even more perplexing. Some fundamental physical processes appear to be reversible, suggesting that time may not always flow in one direction. Yet we experience time as an unstoppable progression forward. Why is this? Despite many laws of physics being symmetric, working equally well in both forward and backward directions, our perception of time remains unidirectional. This ongoing conundrum remains a central puzzle for physicists, underscoring the complexities of time's nature and its pivotal role in shaping both our universe and our experience within it. One of the most captivating aspects of time is the way it is influenced by gravity, revealing the profound interconnection between space and time. This phenomenon, known as gravitational time dilation, is a key prediction of Albert Einstein's theory of general relativity. The theory posits that time is not a fixed, independent entity, but a dimension that can be affected by the gravitational field of massive objects. The stronger the gravitational field, the slower time flows. On Earth, this effect is subtle. Clocks at sea level, where gravity is slightly stronger, tick just a tiny bit slower than clocks located at higher altitudes, where gravity is weaker. In everyday life, this difference is practically imperceptible, but it becomes dramatically apparent in more extreme environments. Near extremely massive objects, such as black holes, the influence of gravity on time is nothing short of dramatic. As an object approaches the event horizon of a black hole, the boundary beyond which not even light can escape, time slows down significantly from the perspective of an outside observer. If you were to watch a clock falling toward a black hole, you would see the clock's ticking slow down as it neared the event horizon. At the very edge of this horizon, time itself would appear to come to a standstill. This warping of time by gravity is not just theoretical, but has profound practical implications. For instance, it must be taken into account in technologies like the Global Positioning System, GPS. Satellites in orbit experience a weaker gravitational field than objects on the Earth's surface, and therefore, time passes more quickly for them. Without accounting for this time dilation, GPS systems would quickly become inaccurate, drifting by several kilometers each day. Space and time are not separate, independent entities. They are intertwined into a single dynamic continuum known as space-time. This revolutionary idea, introduced by Einstein in his theory of relativity, has fundamentally changed the way we view the universe. In this framework, the geometry of space and time is shaped by the presence of matter and energy. Massive objects like stars, planets, and black holes warp the fabric of space-time, and this warping is what we perceive as gravity. Gravity, in this sense, is not a force transmitted through space, but rather the effect of the curvature of space-time itself. The influence of gravity extends beyond just the trajectory of objects moving through space. It also affects the flow of time itself. Near massive objects, time actually runs more slowly compared to regions with weaker gravitational influence. Moreover, the speed at which an object moves through space has a direct impact on how it experiences time. As an object approaches the speed of light, its passage through time slows down relative to a stationary observer. This phenomenon, known as time dilation, has been confirmed through experiments involving atomic clocks on fast-moving aircraft and satellites. Even astronauts aboard the International Space Station experience time slightly slower than we do on Earth, effectively traveling a tiny bit into the future during their missions. This effect, though minuscule, adds up over time, with astronauts aging ever so slightly less than people on Earth. The relationship between space and time also dictates the cosmic speed limit, the speed of light. This universal constant defines the maximum rate at which information or causality can propagate through the universe. Nothing can travel faster than the speed of light, and this restriction forms a crucial boundary in our understanding of the physical world. The intricate connection between space and time shapes the very structure of reality, influencing everything from the motion of planets to the evolution of galaxies, and even the fate of the universe itself. The idea of time travel has fascinated humanity for centuries, becoming a staple of science fiction and speculative thought. While the concept remains far beyond our current technological capabilities, some aspects of time travel are theoretically possible according to our understanding of physics. Einstein's theory of special relativity shows that time can flow at different rates for objects moving at different speeds. This effect, time dilation, has been experimentally verified with atomic clocks placed aboard high-speed aircraft and satellites. Astronauts in space, moving at speeds significantly faster than those on Earth, experience time slightly more slowly, effectively traveling a tiny bit into the future. However, the prospect of traveling into the past remains firmly within the realm of speculation. Though fascinating to consider, time travel, particularly to the past, poses profound theoretical and paradoxical challenges that scientists have yet to unravel. The mysteries of time, though deep and vast, continue to inspire both wonder and curiosity as we push the limits of what we understand about the universe. However, these concepts present far more significant challenges and paradoxes than we might initially imagine. Time travel, long a subject of human fascination, has not only captured the collective imagination of generations, but also posed questions that stretch the very fabric of our understanding of the universe. While some of the solutions to Einstein's field equations in general relativity suggest the possibility of closed time-like curves, loops in spacetime that could, in theory, allow for backward time travel, these ideas require conditions that may not be physically possible in our current understanding. For instance, the existence of exotic matter with negative energy density, a necessary ingredient for these hypothetical time loops, remains speculative at best. From a practical standpoint, the energy requirements and technological hurdles to achieve significant time travel are far beyond what we could accomplish with today's science and engineering. This does not mean, however, that the door to time travel is definitively closed. While time travel remains a theoretical construct, there is always room for future discoveries that might radically alter our understanding of physics and what is possible within it. But for now, time travel is more of a fascinating subject for speculation, a treasure chest of questions that continues to propel both scientific inquiry and philosophical debate, rather than a feasible technological reality. One of the most profound aspects of our experience is the arrow of time, the undeniable direction in which time flows, inexorably moving from the past through the present and into the future. It's a direction that, once set in motion, never appears to reverse or stand still. This perception of time is something we live with every day, whether we're watching eggs break but never unbreak, aging but never growing younger, or remembering the past but unable to see into the future. Time's constant forward march is tied to a fundamental principle of physics: entropy. Entropy measures the amount of disorder in a system. The second law of thermodynamics tells us that in any isolated system, entropy always increases over time. This is why systems naturally evolve towards greater disorder, losing useful energy as they do. The arrow of time is intimately linked to this increase in entropy. As energy spreads out and becomes less concentrated, it creates a distinction between the past and the future. The past has lower entropy than the future, which provides time with its apparent direction. What is most fascinating, though, is that while the arrow of time seems to be a natural and inescapable part of our reality, most fundamental laws of physics are time-symmetric. In other words, they work equally well whether time flows forward or backward. It's only when we consider large systems and the statistical behavior of particles in those systems that the arrow of time makes itself known. This paradox between the time symmetry of the laws of physics at the microscopic level and the unidirectional flow of time at the macroscopic level forms one of the greatest unsolved mysteries of modern physics. This tension is further complicated when we turn to quantum mechanics and relativity, two cornerstones of modern physics that offer strikingly different perspectives on the nature of time. In quantum mechanics, time is treated as a constant backdrop, a uniform and steady parameter within which events unfold. Time, in this framework, does not interact with the quantum events themselves. It is merely the stage on which they occur. This matches closely with our everyday experience of time, a seemingly constant flow, unaffected by the individual events it carries. Relativity, however, completely revolutionizes our conception of time. According to Einstein's theory of general relativity, time is not an absolute universal entity. Instead, it is intimately tied to space, forming a four-dimensional continuum known as spacetime. Time, in this framework, is relative. It is not the same for all observers. Depending on an observer's motion or their proximity to massive objects, the passage of time can vary. One of the most striking consequences of relativity is time dilation, where time moves more slowly for objects that are moving at high speeds or in strong gravitational fields. This introduces a paradox. In one context, Time can appear to flow at different rates, depending on the observer's frame of reference, contradicting our everyday experience of time as a universal constant. This discrepancy between quantum mechanics and relativity creates a profound challenge in theoretical physics. Quantum theory relies on the assumption of a fixed universal time, one that applies across all reference frames, while relativity insists that time is flexible and observer-dependent. Reconciling these two ideas becomes especially problematic in extreme environments, such as the intense gravity of black holes or the conditions that existed at the very beginning of the universe, where both quantum effects and relativistic forces must be taken into account simultaneously. The search for a unified theory of quantum gravity, which can merge these two pillars of modern physics, remains one of the most elusive goals in science today. Among the most intriguing proposals in this quest is the block universe theory, which suggests that past, present, and future all coexist within a four-dimensional block of space-time. This concept challenges our conventional view of time as a flowing entity, where only the present moment is real and the future is yet to unfold. Instead, it posits that all moments in time, past, present, and future, are equally real and permanent, much like locations in space. The theory finds its roots in Einstein's work on special relativity, which showed that the perception of simultaneity varies between observers in different reference frames. What one person experiences as the present might be perceived as the past or future by someone else, depending on their relative motion and position in space. In the block universe model, the flow of time is like a spotlight moving across a film strip. The entire film exists, but we only perceive the illuminated frame as the present. The block universe theory introduces a profound philosophical implication. If the future is already laid out within this four-dimensional block, then our sense of free will, the notion that the future is not yet determined, might be an illusion. According to this theory, all events, whether past or future, are already written into the fabric of space-time. Additionally, the theory offers a possible explanation for the arrow of time's forward progression. It suggests that the perception of time's flow is a result of our limited three-dimensional experience of a four-dimensional reality, rather than an inherent property of time itself. But could time, as we experience it, be an illusion in another sense altogether? Some theorists suggest that time might not be as fundamental as we believe, but rather an emergent property that arises from more basic elements of the universe. This idea challenges the traditional view of time as a linear progression from past to future. According to some of these theories, time emerges from the quantum entanglement between particles. As these particles interact, they produce a sequence of events that we interpret as the flow of time. In this view, the passage of time might not be a fundamental feature of the universe at all, but rather a consequence of deeper, more complex processes at the quantum level. This aligns with the block universe theory, in which the past, present, and future all exist simultaneously. Other scientists suggest that time might be intricately connected to the increase of entropy in the universe. As systems become more disordered over time, we perceive this increase as the passage of time. This relationship between time and entropy could explain why time appears to flow in only one direction, in alignment with the second law of thermodynamics. Although these ideas remain speculative and are a subject of ongoing debate, they open up intriguing possibilities about the nature of time and the universe itself. If time is indeed an emergent property, it could completely transform our understanding of physics, causality, and the very fabric of reality. As we continue to explore these theories, one thing becomes increasingly clear. Our perception of time might be just the tip of a much deeper cosmic iceberg, one whose mysteries we are only beginning to uncover. This exploration takes us into some of the most extreme and mind-bending areas of physics, including near singularities, regions of space-time so dense that they challenge our very understanding of time. These extreme environments, such as those found at the centers of black holes or at the very beginning of the universe, push our physical theories to their breaking points. As we approach a singularity, the gravitational forces are so intense that time itself slows down dramatically. From the perspective of an outside observer, time may appear to freeze altogether at the event horizon of a black hole, leading to profound questions about the nature of time in the most extreme conditions of the universe. In the end, whether we ever unlock the full secrets of time or not, one thing remains certain. Time, with all its paradoxes and mysteries, will continue to be one of the most compelling subjects of scientific inquiry, philosophical debate, and human wonder. When we contemplate the concept of black holes, we are led to a paradox that challenges the very essence of time. For someone falling into a black hole, time would seem to progress in a normal, predictable way, at least from their own perspective. However, from the perspective of an observer outside the black hole, the clock appears to speed up dramatically. This curious discrepancy arises due to the intense gravitational forces near the black hole, where space-time becomes so distorted that the very concept of time itself may lose all meaning. At the singularity, the point of infinite density at the heart of a black hole, our current understanding of physics begins to break down. General relativity, which governs large-scale phenomena, and quantum mechanics, which rules the subatomic realm, both fail to provide a cohesive picture under these extreme conditions. The intense curvature of space-time at the singularity could cause time and space to blend together, erasing the clear distinction between past, present, and future. This boundary, where space-time itself seems to warp beyond recognition, might be even stranger than we imagine. Some theories propose that quantum effects could step in, preventing true singularities from forming. Instead of a point of infinite density, we might encounter a region that is still extremely dense but finite, where space-time adopts a foam-like structure at the smallest scales. In this framework, time could become quantized, existing in discrete, indivisible units rather than flowing smoothly. These potential scenarios not only stretch the limits of our current theories, but also push us to rethink the very nature of time itself. The breakdown of time near singularities highlights just how far we are from understanding the universe in its entirety. It signals a profound gap in our knowledge, suggesting that a new, unified theory, one that merges general relativity with quantum mechanics, is urgently needed. This theory could unlock secrets not only about black holes, but also about the fundamental nature of time itself, perhaps providing a glimpse into what time is at the most basic level. In the quantum realm, a phenomenon known as quantum entanglement offers an equally perplexing view of time. When two particles become entangled, their quantum states are linked in such a way that the state of one cannot be described without referencing the other, no matter how far apart they are. This means that when a measurement is made on one particle, the entangled partner is immediately affected, as if information were transmitted instantaneously across vast distances. This phenomenon seems to defy the speed of light, directly challenging one of the cornerstones of modern physics, Einstein's theory of special relativity. Entanglement raises profound questions about the nature of time and causality. If information can be transmitted faster than light, does this imply that the normal sequence of cause and effect is not always relevant at the quantum level? Additionally, experiments with entangled particles suggest that the order in which measurements are made does not matter, even when those measurements occur at different times. This leads to a striking implication. Quantum correlations could reach backward and forward in time, further blurring the distinction between past, present, and future. Some physicists speculate that quantum entanglement could point toward a deeper truth, that time, as we understand it, may not be a fundamental aspect of reality. Instead, it might be an emergent property of a more profound quantum process. If time is not intrinsic to the universe, but arises from a deeper, more fundamental layer of reality, then our typical understanding of it as a linear progression could be entirely wrong. In this view, the past, present, and future might exist simultaneously in a timeless quantum realm. This brings us to the famous Fermi paradox, which presents a striking mystery in the search for extraterrestrial life. The paradox, named after the physicist Enrico Fermi, arises from a seemingly simple question: where is everybody? Given the vastness of the universe, with its billions of galaxies and trillions of stars, it seems statistically inevitable that intelligent life should have evolved elsewhere. Yet, despite decades of searching, we have found no concrete evidence of extraterrestrial civilizations. No signals, no visits, no signs of life. The absence of evidence for alien civilizations is what makes the Fermi paradox so intriguing. It challenges our understanding of the universe and raises profound questions about the nature of life, technological progress, and the challenges of interstellar communication. There are many theories that attempt to explain this paradox. Some suggest that the conditions required for life are so rare that the emergence of intelligent civilizations is an extraordinary event. Others propose that advanced civilizations may destroy themselves before they achieve the ability to travel between stars. Still others consider the possibility that intelligent civilizations are out there, but for reasons we don't understand, they simply aren't making contact. The question of why we have yet to detect extraterrestrial intelligence is made even more pressing when we consider the factors that should make intelligent life relatively common in the universe. First, there is the sheer size of the cosmos. Our own galaxy contains hundreds of billions of stars, and the observable universe holds trillions of galaxies. This vastness suggests that there are countless potential habitats for life. Furthermore, the discovery of exoplanets has shown that planets are common, no longer the rare cosmic oddity we once thought them to be. Many of these planets exist in the habitable zone of their stars, where conditions could support liquid water on their surfaces, a key ingredient for life as we know it. Moreover, life on Earth emerged relatively quickly after the planet cooled enough to support it. This rapid emergence suggests that, given the right conditions, life might spring into existence far more quickly than we might have previously assumed. The principle of mediocrity, the idea that Earth and its life forms are not exceptional, also implies that similar processes could unfold on other planets. Add to this the extraordinary diversity of life on Earth, with its ability to adapt and thrive in even the most extreme environments, and it becomes clear that there is ample opportunity for intelligence to evolve elsewhere in the universe. Despite these factors, the Fermi paradox remains a mystery. Scientists and thinkers have proposed several intriguing solutions. One possibility is the Great Filter hypothesis, which suggests that there is a significant insurmountable obstacle that prevents life from evolving into civilizations capable of interstellar travel. This filter could be a difficult step in the evolution of life, a tendency for intelligent species to self-destruct, or an unknown cosmic event that periodically wipes out advanced life. Another explanation is the zoo hypothesis, which posits that advanced alien civilizations are aware of our existence but deliberately choose not to make contact. Instead, they observe us as we might observe animals in a zoo, waiting for us to reach a certain level of technological or social development before initiating communication. The rare Earth hypothesis takes a different approach, suggesting that the conditions necessary for complex life are so rare that Earth itself is a unique oasis in a largely barren universe. These theories, along with the Fermi paradox, highlight the profound mysteries we face as we explore the cosmos. The Drake equation, which attempts to estimate the number of detectable civilizations in our galaxy, provides an optimistic view, suggesting that there could be many advanced civilizations out there. But the fact that we have yet to encounter any remains a tantalizing, unresolved enigma. The search for extraterrestrial life continues, and with it, our quest to understand our place in the vast, enigmatic universe. However, this takes us directly to the enigmatic Fermi paradox, named after the physicist Enrico Fermi. The paradox presents a deceptively simple, yet profoundly unsettling question. If there are so many potential alien civilizations scattered across the vast expanse of the universe, why have we not detected any signs of their existence? This paradox brings into sharp contrast the optimistic predictions suggested by the Drake equation with the stark reality of our observations, which have yet to reveal any definitive evidence of extraterrestrial intelligence. The equation, which estimates the number of active, communicative extraterrestrial civilizations in the Milky Way, suggests that the universe is teeming with life. Yet, our ongoing search for extraterrestrial signals and encounters has yielded nothing substantial. The question arises, why? This glaring contradiction between the promising forecasts of the Drake equation and the silence of the cosmos forms the heart of the Fermi paradox. While the equation paints a picture of an abundant universe brimming with alien life, our reality shows only an eerie absence. This disparity has inspired a wide array of hypotheses, each attempting to explain why, despite the statistical likelihood of life elsewhere, we have not encountered other civilizations. Some suggest that life is exceedingly rare, that the conditions necessary for intelligent beings to emerge are so improbable that our own existence might be a cosmic fluke. Others propose more pessimistic scenarios, such as the possibility that advanced civilizations invariably destroy themselves, perhaps through warfare, environmental collapse, or runaway technology, before they can reach out to others. The relationship between the Drake equation's projections and the silence we hear continues to fuel intense debate and speculation. Scientists are tirelessly refining the parameters of the equation and developing more sophisticated search strategies to probe the cosmos for any trace of intelligent life. In this ongoing effort, researchers are constantly pushing the boundaries of our understanding of life in the universe, expanding both the scope and depth of the search for extraterrestrial intelligence. One of the most intriguing theories proposed to address the Fermi paradox is the Great Filter hypothesis. This concept, central to the study of astrobiology, posits that there are certain critical stages or hurdles that a civilization must overcome in its evolution before it becomes capable of interstellar travel or colonization. These hurdles might include the emergence of life itself, the rise of complex organisms, the development of intelligence, or the mastery of advanced technologies capable of enabling space travel. According to the Great Filter theory, the reason we have not encountered other civilizations is that the process of evolution is far more challenging than we imagine. One or more of these stages are so difficult to traverse that only a tiny fraction of civilizations ever manage to make it to a point where they can venture beyond their home worlds. If the Great Filter lies behind us, it suggests that humanity has already passed through the most difficult stages of evolution, making us one of the rare exceptions to a universal rule. In this scenario, the absence of other civilizations could simply be because most other species have failed to make it through these stages, meaning that we're effectively alone in the galaxy. On the other hand, if the Great Filter lies ahead of us, it suggests a much darker possibility, that there is a significant challenge or catastrophic event awaiting us, one that typically causes advanced civilizations to self-destruct. This could take the form of nuclear war, uncontrolled climate change, or other unforeseen consequences of technological advancement. The idea that the most difficult stage may still lie in our future raises unsettling questions about the sustainability of our own civilization. The Great Filter hypothesis not only influences our understanding of the Fermi paradox, but also compels us to examine the potential obstacles that may lie in our future as a species. It forces us to confront both the rarity of intelligent life and the potential perils that await us as we continue to develop technology at an unprecedented rate. In this context, our search for extraterrestrial intelligence is as much about understanding our own future as it is about discovering life elsewhere in the cosmos. Another captivating theory in the search for alien life is the zoo hypothesis, which suggests that extraterrestrial civilizations may be deliberately concealing their presence from us. According to this theory, advanced alien societies might be observing Earth from afar, choosing not to make contact with our relatively primitive civilization. Much like how we observe animals in a zoo or study wildlife in nature preserves, these civilizations might be conducting long-term, hands-off scientific studies, allowing us to evolve and develop naturally without interference. There are several reasons why such civilizations might choose to remain hidden. One possibility is that they could be protecting us from knowledge or technology that our society is not yet capable of understanding or safely using. The discovery of such advanced ideas could destabilize our society or lead to disastrous consequences. Alternatively, they may simply be following a policy of non-interference, allowing us to develop on our own without their involvement. Another theory suggests that these civilizations might possess stealth technologies that are far beyond our current understanding, making it possible for them to remain hidden despite our attempts to detect them. They could be using methods to shield their emissions, cloak their planets, or even manipulate the fabric of space-time itself, effectively rendering themselves invisible to our detection techniques. However, it is essential to recognize that all of these ideas remain speculative. The vastness of the universe and the limitations of our technology make it incredibly difficult, if not impossible, to confirm the existence of such hidden civilizations. Despite our best efforts to probe distant stars and detect faint signals, we have yet to uncover definitive evidence of extraterrestrial life, let alone intelligent beings deliberately evading detection. But with future advancements in technology and methodology, it's possible that we may one day uncover something that is currently beyond our reach. Interstellar travel is another major factor that complicates our understanding of the Fermi paradox. The enormous distances between stars present a formidable barrier for any civilization attempting to explore, colonize, or even communicate across the galaxy. Even at speeds approaching the speed of light, a feat that is currently far beyond our capabilities, journeys to neighboring star systems would take many years, if not decades. The logistical challenges of such voyages are staggering, requiring spacecraft capable of sustaining life for generations and providing all the necessary resources for extended missions. The energy required to accelerate to relativistic speeds and then to decelerate upon reaching a destination would exceed our current energy production capacity by orders of magnitude. Additionally, navigating and communicating across these vast distances is a monumental challenge. The precision required to target a distant star system is extraordinary, and the communication delays caused by the sheer scale of interstellar space would make real-time interaction impossible. These immense challenges suggest that the ability of any civilization to spread across the galaxy is likely to be severely limited. The fact that we have not observed clear evidence of extraterrestrial civilizations may, in part, be due to these very constraints of interstellar travel. The vast distances, along with the complexities of sustaining long-term missions and maintaining communication, could explain why, even if intelligent life is widespread, we have not yet encountered it. However, these constraints also open the door to alternative possibilities. Rather than physical interstellar travel, advanced civilizations may choose to explore the galaxy through self-replicating probes, which could be sent out to distant star systems to gather information or even colonize new worlds. These probes could replicate themselves upon arrival, creating entire fleets capable of reaching far-flung corners of the galaxy without requiring a civilization to physically journey to each location. Alternatively, civilizations might develop virtual or simulated experiences of other worlds, sidestepping the need for physical expansion. Some even speculate that future technologies might enable breakthroughs in our understanding of physics and space-time, allowing civilizations to travel across vast distances in ways we cannot yet imagine. The age of the universe itself plays a crucial role in shaping the Fermi paradox. With an estimated age of 13.8 billion years, the universe has had more than enough time for life to arise and evolve on countless planets. This extensive time frame suggests that if intelligent life is common, some civilizations could have had billions of years to develop advanced technologies and spread across the galaxy. Even with slower than light travel, an advanced species could theoretically colonize the entire Milky Way within a few million years, a mere blink in cosmic terms. Yet, despite the seemingly vast opportunity for such civilizations to emerge and expand, we still see no signs of widespread colonization or any definitive evidence of intelligent life. This raises profound questions. Are we truly alone in the galaxy, or are there limits to the extent that civilizations can explore or communicate across such vast distances? The age of the universe amplifies the mystery, as it suggests that if extraterrestrial civilizations exist, they would have had more than enough time to make their presence known. And yet, their absence continues to puzzle us. The age of the universe is not just a measure of time. It is intricately connected to the very building blocks of life as we understand it. Early stars, in their violent and energetic life cycles, forged the heavier elements necessary for life through the process of nuclear fusion. These elements, including carbon, oxygen, and nitrogen, are the fundamental components that make up the molecules of life. Over the course of billions of years, subsequent generations of stars enriched the cosmos further, spreading more complex atoms throughout space. It is this cosmic evolution, this gradual accretion of elements, that created the conditions needed for life to emerge on Earth. And yet, this unfolding story of star formation and element creation raises a profound question: why, in such an ancient and element-rich universe, seem to be alone? The search for extraterrestrial intelligence, SETI, has become one of the most ambitious scientific endeavors in the modern era. Scientists approach this question from multiple angles, combining the power of astronomy, cutting-edge technology, and innovative thinking. One of the primary methods in the search for extraterrestrial intelligence is radio astronomy, where massive radio telescopes are employed to scan the vast expanse of the universe for artificial signals. These signals, potentially originating from alien civilizations, would stand out from the natural cosmic background noise. Instruments like the Allen Telescope Array in California are specially designed to detect narrowband radio emissions, which could be a form of communication from intelligent beings far beyond our own solar system. But the search does not stop there. Optical searches also play a critical role in the hunt for extraterrestrial life. Astronomers now use sophisticated instruments to look for brief, intense flashes of light that could signify laser communications from technologically advanced civilizations. In addition to these direct searches for signals, scientists also turn their attention to the light emitted by distant stars. This light can reveal a wealth of information about the stars themselves and the potential presence of megastructures, hypothetical constructs like Dyson spheres, which might be built by advanced civilizations to harness the full energy of their stars. The discovery of such structures would be a clear indicator of highly advanced alien societies. Another crucial aspect of the search for life beyond Earth lies in the study of exoplanets, planets that orbit stars outside our solar system. As we discover and analyze these distant worlds, scientists are particularly focused on identifying biosignatures in the planet's atmospheres. These are chemical markers that might point to the presence of life, and if found, could suggest that life, perhaps even intelligent life, exists elsewhere in the universe. The search extends beyond distant stars to our own solar system as well. Missions to Mars and the moons of Jupiter and Saturn are actively searching for microbial life, which could offer critical clues about the conditions that foster intelligence elsewhere in the cosmos. At the cutting edge of the search for extraterrestrial intelligence, projects like the Breakthrough Listen initiative are pushing the boundaries of what we can achieve. This initiative uses powerful computers to analyze massive amounts of data gathered by telescopes around the world, searching for patterns that could suggest the presence of extraterrestrial technologies. As our methods and technologies advance, we continue to expand our cosmic exploration, driven by the profound question: are we alone in the universe? The question of whether humanity is alone in the universe is one of the most profound and enduring mysteries in science. The universe, with its billions of galaxies, each containing billions of stars, is staggeringly vast. Given this scale, it seems increasingly unlikely that Earth is the only planet to harbor life. Yet despite this vastness, we have not yet discovered definitive evidence of life beyond our planet. This silence has led some to propose the rare Earth hypothesis, which suggests that the specific conditions required for life, especially complex intelligent life, are exceptionally rare. These conditions include factors such as the right distance from a stable star, a protective magnetic field, and the presence of a large moon to stabilize the planet's axis. If we are indeed alone, it could mean that Earth is not only rare, but uniquely suited to harbor life. The implications of such a discovery would be profound. If humanity is the only intelligent species in the universe, it would place on us an immense responsibility to be the custodians of consciousness and intelligence in the cosmos. Our planet would not just be rare, it would be one of a kind, and this fact would make the preservation of Earth and its ecosystems not just important, but paramount. At the same time, the realization that we are alone in the universe might drive humanity to explore and perhaps even colonize other worlds, ensuring the continuation of life beyond Earth. Yet, it is important to remember that our search for extraterrestrial life is still in its infancy. We have only just begun to scratch the surface of our own solar system, let alone the countless other star systems in our galaxy. As our technology advances and our understanding of the cosmos deepens, we may yet uncover evidence that we are not alone, forever altering our perspective on our place in the universe. One of the most fascinating and perplexing phenomena at the forefront of modern physics is quantum entanglement. At its core, this phenomenon describes the strange connection between particles that allows them to instantaneously influence each other, regardless of the distance separating them. This behavior challenges our traditional understanding of space, time, and causality. In the quantum world, particles can become entangled in such a way that the state of one particle is directly linked to the state of another, even when they are separated by vast distances. When we measure the state of one entangled particle, we instantaneously know the state of its partner, no matter how far apart they are. This strange behavior was famously described by Albert Einstein, who referred to it as spooky action at a distance. Einstein struggled to accept the idea that information could travel faster than light, a notion that contradicted his theory of special relativity. However, over the years, numerous experiments have confirmed the reality of quantum entanglement. These experiments have shown that particles can indeed influence each other instantaneously, regardless of the distance between them. This discovery has profound implications for our understanding of the nature of reality itself and the fundamental principles that govern the universe. Quantum entanglement is not just a theoretical curiosity. It has practical applications that could revolutionize fields such as quantum computing, cryptography, and the transmission of quantum information. In the future, quantum entanglement may even lead to the development of technologies that allow for the instantaneous transmission of information across vast distances, potentially altering the way we think about communication and information processing. As we continue to explore the strange and mysterious realm of quantum mechanics, we may uncover even more surprising revelations about the fabric of our universe, revealing that reality is far stranger and more interconnected than we could have ever imagined. Quantum entanglement stands as one of the most profound and perplexing phenomena in the realm of modern physics. While the principles behind it seem to defy the very fabric of our classical understanding, the experimentations that have been conducted over the past several decades have not only confirmed its existence, but also showcased its far-reaching implications on how we perceive the universe. The consequences of entanglement extend well beyond the confines of particle physics, raising fundamental questions about the nature of reality, space-time, and the interconnectedness of all things in the cosmos. At its core, quantum entanglement refers to a process where two or more particles become so deeply linked that the quantum state of one particle cannot be fully described without taking into account the state of its entangled counterpart. Remarkably, this connection remains intact even when the particles are separated by vast distances that span across the universe. The mere idea that two particles can instantaneously affect one another, no matter how far apart they are, challenges everything we thought we knew about space and time. However, scientists have shown that although it appears as though information is being transferred faster than light, no actual information is being sent in the traditional sense. This preservation of the cosmic speed limit dictated by the theory of special relativity prevents any violation of fundamental laws of physics. Still, the implications of quantum entanglement challenge our basic notions of locality and realism, suggesting that the universe may not be as separate and independent as we once assumed. Instead, it presents the possibility that everything might be far more interconnected than we previously dared to imagine. Some interpretations of quantum mechanics even go as far as proposing that quantum entanglement could imply the existence of multiple parallel universes or alternate realities. The idea that reality only takes shape when we observe it, that the act of observation itself brings the universe into being, is another profound notion tied to entanglement. These mind-bending concepts force us to rethink not just the nature of reality, but our very place within it, inviting us to consider that the universe is a far stranger and more mysterious place than we ever could have imagined. The EPR paradox, proposed in 1935 by physicists Albert Einstein, Boris Podolsky, and Nathan Rosen, encapsulates this very conundrum. Their thought experiment was designed to question the completeness of quantum theory, particularly its implications for the principle of locality in physics. Local realism, the idea that objects have definite properties independent of measurement, and that no information can travel faster than light, seemed incompatible with the bizarre predictions made by quantum mechanics. In the EPR paradox, two particles are entangled, meaning that measuring one particle instantaneously determines the state of the other, regardless of the distance between them. This instantaneous connection defies the principle of locality and challenges our understanding of the nature of information and reality. Einstein, who famously referred to this phenomenon as spooky action at a distance, was troubled by the apparent conflict between quantum mechanics and his own theory of relativity. He, Podolsky, and Rosen argued that quantum mechanics could not be complete because it allowed for what seemed to be faster-than-light communication. This argument sparked decades of debate and inquiry into the validity of quantum mechanics, leading to groundbreaking developments in the field. Over the years, however, experimental tests have overwhelmingly supported the reality of quantum entanglement. Through increasingly sophisticated experiments, scientists have demonstrated that entangled particles exhibit the peculiar behavior predicted by quantum mechanics. One of the most famous experiments involved entangled photons, which were created and separated across large distances. When the properties of one photon were measured, the properties of its distant partner could be determined instantly, even when the two particles were separated by hundreds of kilometers. This experiment, among many others, confirmed that the strange behavior of entangled particles is not merely a theoretical construct, but a tangible phenomenon that can be observed in the laboratory. Another crucial test that verified the existence of quantum entanglement involved the violation of Bell's inequalities. These mathematical relationships, proposed by physicist John Bell in the 1960s, set limits on the degree of correlation that could be observed between particles in classical physics. When entangled particles were measured, they consistently violated these inequalities, demonstrating behavior that cannot be explained by classical theories alone. Such results not only validated the principles of quantum mechanics, but also reinforced the strange, non-local behavior of entanglement. As our understanding of entanglement deepens, scientists have gone further by achieving entanglement between larger and more complex systems, such as atoms and even tiny mechanical devices. These experiments represent a significant step toward bridging the gap between the quantum world and the macroscopic world we experience in our daily lives. They suggest that quantum phenomena might not be confined to the microscopic realm, but could have far-reaching applications in fields that directly impact our lives. One such application is quantum teleportation, a process in which quantum information is transferred from one location to another without the need to move the physical particle itself. Unlike the science fiction depiction of teleporting matter, quantum teleportation relies on the entanglement of two particles. The sender measures the state of one particle in the entangled pair, which destroys its quantum state, but provides crucial information. This information is then transmitted through classical communication channels to the receiver, who uses it to manipulate their half of the entangled pair, effectively recreating the original quantum state. While this process does not involve the faster-than-light transmission of energy or matter, it holds immense potential for secure communication and quantum computing, offering a glimpse into the future of technology. Quantum entanglement also holds tremendous promise for revolutionizing fields like computing and communication. In quantum computing, entangled particles enable qubits, the quantum analog of classical bits, to exist in multiple states simultaneously. This ability to process information in parallel allows quantum computers to solve problems that would take classical computers millions of years to crack. From drug discovery to financial modeling and climate prediction, the potential applications of quantum computing are vast and transformative. Moreover, entangled particles could enhance the security of communications in ways previously unimaginable. Quantum key distribution, for example, uses the principles of entanglement to create encryption keys that are virtually impossible to intercept without detection. Any attempt to measure or observe the entangled particles disrupts their state, alerting users to potential eavesdropping attempts. This could usher in an era of virtually unbreakable cybersecurity. Furthermore, quantum entanglement could lead to the development of ultra-sensitive sensors with applications in navigation, medical imaging, and even resource detection. Entangled particles could be used to create magnetometers or gravimeters that are capable of measuring extremely subtle changes in magnetic fields or gravitational forces, paving the way for new technologies in a variety of fields. All these developments raise profound philosophical questions about the nature of reality itself. The principle of non-locality, suggesting that particles can influence one another instantaneously, regardless of distance, defies our classical intuition, in which we assume that interactions are limited by the speed of light. Quantum mechanics upends this understanding, presenting a reality in which space and time may not behave as we expect. Entanglement, as one of the most striking manifestations of this non-locality, forces us to reconsider the very nature of the universe, suggesting a level of interconnectedness that transcends the boundaries of space and time. As we continue to explore the mysteries of quantum entanglement, we are not just delving into the fabric of the universe at the microscopic scale, we are challenging our most fundamental assumptions about the very nature of existence. The universe, it seems, may be far more complex, interwoven, and mysterious than we could ever have imagined. However, numerous experiments over the years have solidified the reality of non-locality, forcing scientists to rethink and recalibrate their most foundational understanding of space, time, and causality. This mind-bending phenomenon has opened doors to an entirely new way of understanding the universe, suggesting that at its most fundamental level, reality is far more interconnected and complex than previously thought. Non-locality, in the context of quantum mechanics, implies that particles can influence each other instantaneously, no matter how vast the distance between them, an implication that directly challenges the conventional limits set by the speed of light. This revelation continues to perplex not only physicists, but also philosophers, emphasizing the mysterious and often counterintuitive nature of the quantum world. At the heart of this mystery is quantum entanglement, a phenomenon so perplexing that it has led many scientists to explore its potential connections to something as elusive as consciousness. Quantum entanglement occurs when particles become linked in such a way that the state of one particle is directly related to the state of another, even when they are light years apart. The idea that two particles can share such a deep, instantaneous connection, despite being separated by astronomical distances, is difficult to reconcile with our everyday experiences of space and time. Some researchers, intrigued by this profound entanglement, have speculated that the same quantum processes responsible for this strange connection might also play a role in consciousness. Could it be that the consciousness we experience in our minds might in some way arise from quantum processes happening within the brain? This theory posits that the vast network of neurons in the brain could potentially harbor quantum effects that allow for instantaneous processing of information, a kind of processing that might help explain the unified, continuous nature of conscious experience. This hypothesis is bold and speculative, and many scientists remain highly skeptical. The brain, being a warm, wet environment, is thought to be inhospitable to the delicate quantum states required for such processes. In such a dynamic and fluctuating setting, quantum states are expected to lose their coherence too quickly to have any lasting impact. Critics argue that classical physics, together with neurobiology, is more than sufficient to explain how the mind works, and that invoking quantum mechanics might be unnecessary and distracting. However, this does not deter those who continue to explore the potential connections between the quantum realm and consciousness. The ongoing research into this fascinating intersection of quantum mechanics, neuroscience, and philosophy continues to push the boundaries of human knowledge, offering tantalizing glimpses of what might be a far deeper and more intricate relationship between the brain and the universe. Despite the uncertainty, the quest to understand this potential link could redefine not just our understanding of the mind, but also the very nature of reality itself. As this debate rages on, quantum entanglement is also proving to have immense potential beyond the realm of theoretical physics. It holds the key to a future in which computers, networks, and security could be fundamentally transformed. At the heart of this transformation lies quantum computing, an area of research that exploits the power of entangled particles to perform calculations at speeds far beyond what is possible with classical computers. In essence, quantum computers can solve complex problems that are currently intractable with traditional computing methods, offering new possibilities in fields like drug discovery, financial modeling, climate prediction, and many others. But quantum entanglement does not stop there. It also forms the foundation for a new era of secure communication through the burgeoning field of quantum cryptography. This technology could offer a level of security that completely surpasses current encryption methods. The key to this unbreakable security lies in the fact that any attempt to measure or intercept the entangled particles would immediately disrupt their delicate quantum state, alerting both parties involved to the breach. Such a mechanism offers an unprecedented level of protection for sensitive data and communications, offering a future where cyber threats may become an issue of the past. Moreover, the strange phenomenon of quantum entanglement has opened up the possibility of quantum teleportation, an idea straight out of science fiction, but one that may have real-world applications. Though quantum teleportation does not involve the physical transport of matter, it could enable the instantaneous transfer of quantum information across vast distances. This could be crucial for the development of quantum networks and, eventually, a true quantum internet. Such a network would revolutionize the way we transmit data, offering lightning-fast speeds and unparalleled security for global communication. It's a breakthrough that could radically alter the technological landscape of the future, although we're still in the early stages of this development. However, it is essential to clarify a key point. While quantum entanglement does allow for instantaneous correlations between entangled particles, this does not imply that it could be used to transmit information faster than the speed of light. The idea of using quantum entanglement for telepathy or similar paranormal claims is not supported by scientific evidence. Despite the fascination with such ideas, there is no current evidence to suggest that entangled particles can transfer meaningful information faster than light. Quantum entanglement operates on subatomic scales and does not in any direct way apply to the macroscopic world of human consciousness or communication. In fact, scientists have rigorously tested claims of telepathy and other paranormal phenomena, but the results have consistently failed to produce reliable, reproducible evidence to support such ideas. While quantum mechanics can seem mysterious, especially in its more counterintuitive aspects, it is crucial that we approach such claims with skepticism and rigor, relying on the scientific method and empirical evidence to guide our understanding rather than extrapolating quantum effects into unrelated domains. One of the most enduring challenges within quantum mechanics is the so-called measurement problem. At its heart, this problem stems from the stark contrast between the predictions made by quantum theory and the observations we make in the real world. According to quantum mechanics, particles can exist in multiple states at once. This is known as superposition. An electron, for example, could be spinning both clockwise and counterclockwise at the same time, according to quantum theory. But when we measure its spin, we only ever observe it in one definite state, either clockwise or counterclockwise, never both. This sudden collapse from a state of multiple possibilities to a single reality is what is known as the collapse of the wave function. The measurement problem asks, why does this collapse happen and what causes it? Does the act of measurement itself force the quantum system to select a particular state, or is there some unknown mechanism at play that we don't yet understand? Various interpretations of quantum mechanics have been proposed to address this issue, such as the many worlds interpretation, which posits that all possible outcomes actually occur in parallel universes, or the Copenhagen interpretation, which suggests that the act of measurement itself causes the wave function to collapse. These interpretations represent different ways of understanding a puzzle that has confounded physicists for decades, and which continues to shape the course of quantum theory as we know it. However, despite decades of research, debate, and profound philosophical inquiry, the measurement problem remains one of the most perplexing and contentious issues in modern physics. It challenges our understanding of reality at its most fundamental level. The nature of observation, particularly in quantum systems, plays a pivotal role, one that fundamentally alters the behavior of particles at the subatomic scale. In the quantum world, particles are not just points with specific locations or properties. They exist in a state of flux, a sea of probabilities, where the act of observation directly influences the system itself. This raises questions about the very nature of reality and the role of consciousness in shaping the universe. When we observe a quantum system, we inevitably interact with it. This interaction causes what physicists refer to as wave function collapse, a phenomenon that turns the quantum state from a superposition, a collection of potential possibilities, into a single definite outcome. Before an observation, quantum particles exist in a state of uncertainty described by wave functions that represent all possible outcomes simultaneously. This can be difficult to visualize, but it's crucial in understanding the inherent nature of quantum systems. The famous Schrödinger's cat thought experiment illustrates this principle. In an isolated box, a cat can be both alive and dead at the same time, a bizarre yet illustrative example of superposition. It is only when we observe the cat that its state collapses into one of the two possibilities, alive or dead. Similarly, quantum particles can occupy multiple positions or exhibit various properties at once. It is only through the act of measurement that the quantum system is forced to choose one of these possible states. This is not simply a matter of uncovering a pre-existing truth about the system. The act of observation itself shapes the outcome, influencing the system in a profound way that defies classical understanding. In essence, the observer effect in quantum mechanics goes far beyond the classical idea of measurement disturbing a system. It suggests that the act of measurement fundamentally alters the reality of that system at the quantum level. This principle raises profound philosophical questions about the nature of existence and reality. It suggests that the universe may not be deterministic at its smallest scales, and that consciousness, through the act of observation, plays an active role in shaping the physical world around us. This interplay between the observer and the observed continues to be a central subject of study and debate in the field of quantum mechanics, with scientists striving to understand the true nature of reality itself. The process of wave function collapse is a central concept in quantum mechanics, offering a glimpse into how reality might behave at the smallest, most fundamental levels of existence. Wave function collapse occurs when we observe or measure a quantum system. Before measurement, the quantum system exists in a state of superposition, where it encompasses all potential outcomes that the wave function can represent. Yet, when an actual measurement takes place, the system seemingly collapses into a single, definite state. The debate surrounding this collapse is rooted in its paradoxical nature and the philosophical questions it raises. Some scientists argue that the collapse is a real, physical process that occurs when a quantum system interacts with a classical measuring device, while others believe that it is merely a mathematical description of our changing knowledge about the system, rather than a physical event. This division touches on some of the most profound questions in philosophy and physics. Is consciousness required to collapse the wave function, or is measurement simply an observer-independent process that happens when certain conditions are met? The answers remain elusive, despite years of research. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, accept wave function collapse as an essential feature of quantum mechanics, while others, such as the many worlds interpretation, reject it entirely. According to the many worlds view, the wave function never collapses, but rather splits into multiple parallel realities, each corresponding to a different outcome of the quantum measurement. The controversy surrounding wave function collapse is further exacerbated by the fact that we dare not directly observe the collapse process itself. This inability to witness the collapse leaves ample room for various interpretations, leading to ongoing debates about the true nature of quantum reality. Even though decades of research and discussion have been dedicated to this issue, there remains no consensus among physicists about how to resolve these fundamental questions about wave function collapse and its implications for our understanding of the universe. As a result, the measurement problem continues to be one of the most profound and unresolved issues in modern physics. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, is one of the most influential perspectives in quantum mechanics. It addresses the peculiar and often counterintuitive nature of quantum phenomena by proposing that quantum systems exist in a state of superposition. This means that before measurement, all potential outcomes coexist simultaneously. The superposition state only collapses into a definite result when an observation or measurement is made. This interpretation challenges classical notions of reality, suggesting that measurement itself plays a crucial role in determining the outcome of quantum events. A central tenet of the Copenhagen interpretation is the idea of wave function collapse. The wave function, which represents the probabilities of all possible states, collapses into a single definite state once a measurement is made. This interpretation emphasizes the probabilistic nature of quantum mechanics, asserting that we can only predict the likelihood of various outcomes rather than determine them with absolute certainty. The Copenhagen interpretation also suggests that the quantum world is fundamentally indeterminate and that classical concepts of causality and determinism no longer apply at the quantum scale. This perspective has had a profound influence on how scientists approach the mysteries of the quantum realm, but it has also sparked decades of debate. The Copenhagen interpretation suggests that the quantum world behaves in ways that are fundamentally different from the classical world we experience daily, challenging our most basic assumptions about how reality works. Despite its widespread acceptance, it remains the subject of intense scrutiny and criticism, with many questioning whether it offers a complete picture of quantum reality. The many worlds interpretation, proposed by Hugh Everett in the 1950s, offers a radically different solution to the measurement problem in quantum mechanics. This theory suggests that, rather than collapsing into a single outcome, every possible outcome of a quantum measurement actually occurs. However, these outcomes do not coexist in a single reality. Instead, the universe splits into multiple parallel realities, each corresponding to one of the possible outcomes. In this view, the wave function never collapses. Instead, it continues to evolve, with each possible outcome existing in a separate parallel universe. This approach eliminates the need for a special process of measurement or observation to cause the wave function to collapse. Instead, measurement simply entangles the observer with the quantum system, creating multiple versions of the observer, each experiencing a different outcome. The many worlds interpretation thus removes the distinction between the quantum and classical worlds, suggesting that the two are not separate but part of a larger, interconnected multiverse. However, the many worlds interpretation is not without its critics. The most significant challenge to this theory is the issue of unobservable parallel universes. Critics argue that the existence of these parallel realities cannot be verified through observation or experiment, making the theory difficult to accept. Nevertheless, the many worlds interpretation offers an intriguing and radical solution to the measurement problem, one that continues to provoke debate and challenge our understanding of quantum reality. In the end, the measurement problem remains one of the most profound mysteries in modern physics, with no consensus on how to resolve it. Whether the wave function collapses, whether multiple realities exist, or whether consciousness plays a central role in determining the outcome of quantum events, these questions continue to provoke intense philosophical and scientific inquiry. As research continues, the answers to these questions may ultimately reshape our understanding of the universe and our place within it. However, proponents of alternative interpretations of quantum mechanics argue that their models provide a more consistent and universally applicable description of the phenomenon. These interpretations sidestep the need for arbitrary rules concerning measurement and the so-called collapse of quantum states, helping to simplify what has long been a deeply puzzling issue. Despite these efforts, the debate remains unresolved, underscoring the ongoing challenge faced by physicists in reconciling the behavior of quantum systems with the everyday world we experience. At the heart of this challenge lies quantum decoherence, a fundamental process in quantum mechanics that offers an essential explanation for how quantum systems lose their delicate superposition states when interacting with the environment. Decoherence happens when a quantum system's wave function becomes entangled with its surroundings, causing the information about its quantum state to spread out and become effectively classical. In essence, quantum coherence, the ability of particles to exist in a superposition of multiple states simultaneously, is gradually lost, and the system behaves more like a classical object. The measurement problem in quantum mechanics, one of the central dilemmas in the field, highlights the mysterious question of why we observe distinct, definite outcomes during measurements, despite the quantum theory's prediction that particles can exist in a superposition of states. This conundrum persists at the very heart of quantum mechanics. Quantum decoherence steps in here as a crucial bridge between these seemingly contradictory ideas, those of quantum theory and the classical everyday world. As quantum systems interact with their environment, information about their states leaks out and the system's quantum coherence deteriorates. This rapid loss of coherence explains why we never see quantum superpositions in macroscopic objects. Larger systems lose their quantum nature so quickly that it is practically impossible to observe them behaving in a quantum mechanical manner. However, decoherence does not offer a complete solution to the measurement problem. While it accounts for why we only observe certain stable states that align with classical reality, it doesn't fully explain the collapse of the wave function during measurement. Rather, decoherence helps us understand why macroscopic objects, such as chairs, cars, and people, follow the deterministic laws of classical physics, even though the fundamental particles that compose them abide by quantum rules. It selects a range of preferred states that are stable under environmental interactions, and this selection aligns with the classical properties we observe in our everyday lives. Despite its utility, quantum decoherence leaves some critical questions unanswered, especially regarding the precise mechanism by which quantum systems become classical. As quantum theory continues to probe these unresolved questions, it shines a light on a deep rift between the behavior of the quantum world and the classical world we experience. The measurement problem at the center of quantum mechanics raises profound questions not only about the nature of the universe, but also about the very act of observation itself. In quantum mechanics, before a measurement, particles exist in a superposition where they occupy multiple states at once. However, once measured or observed, these particles suddenly choose a single state. This puzzling shift raises questions about what happens during observation. Is it the act of measurement that causes the particle to collapse into a single state, or does the particle exist in all states until we observe it? These questions fundamentally challenge our understanding of reality. The measurement problem extends beyond the realm of quantum particles, suggesting that our very act of observing could be influencing the outcome of experiments, blurring the boundary between the observer and the observed. This observation-based interference challenges the traditional notion of an objective reality, one that exists independently of human perception or measurement. It implies that what we consider real might be more intricately tied to our acts of observation than we had previously understood. Furthermore, this paradox underscores the limitations of our current grasp of quantum mechanics, despite its extraordinary predictive power. The theory, although successful in many respects, remains deeply mysterious when it comes to the specifics of wave function collapse during measurement, leaving an intellectual void that continues to spark debate. The role of consciousness in quantum mechanics adds another layer of complexity to the measurement problem. Some interpretations, notably the Copenhagen interpretation, suggest that consciousness might be key to the collapse of the wave function, implying that only when a conscious observer measures the quantum system does it choose a definite state. According to this view, quantum systems exist in a superposition of states until observed by a conscious entity, which forces the system to assume a single definite state. This notion raises profound philosophical questions about the relationship between the mind and physical reality. Critics, however, argue that introducing consciousness as a fundamental element of quantum mechanics complicates the theory unnecessarily and anthropocentrically. They point out that it's challenging to define precisely when a conscious observer becomes relevant in the measurement process, and at what stage consciousness influences the collapse of the wave function. In contrast, other interpretations, such as the theory of decoherence, attempt to explain the measurement problem without invoking consciousness, instead focusing on environmental interactions and the loss of quantum coherence. Nevertheless, the idea that consciousness may play a role in quantum measurements continues to intrigue both physicists and philosophers alike, as it highlights the unresolved mysteries at the intersection of quantum mechanics, consciousness, and the nature of reality itself. Quantum mechanics, the cornerstone theory explaining the behavior of matter and energy at the most minuscule scales, has spurred a variety of interpretations, each of which holds profound implications for our understanding of parallel universes. Among the most famous is the many worlds interpretation proposed by Hugh Everett, which suggests that every quantum event spawns multiple parallel universes. According to this view, all possible outcomes of a quantum measurement are realized, but each in a different universe. This interpretation implies the existence of an infinite number of parallel realities, all branching off from each quantum interaction. On the other hand, the Copenhagen interpretation, one of the oldest and most widely accepted views, argues that quantum systems exist in a superposition of states until they are measured or observed. Unlike the many worlds interpretation, the Copenhagen view does not necessarily imply the existence of parallel universes. Instead, it highlights the probabilistic nature of quantum mechanics, suggesting that reality is not fully determined until the wave function collapses, potentially limiting the concept of parallel universes. Another perspective is provided by pilot wave theory, also known as Bohmian mechanics, which posits that particles have definite positions and trajectories, guided by a real physical wave. While this interpretation maintains a single universe, it introduces the idea of non-locality, the notion that particles can instantaneously influence one another, regardless of the distance separating them. Although pilot wave theory does not support parallel universes in the traditional sense, it challenges our understanding of space, time, and the nature of physical reality. The measurement problem in quantum mechanics remains one of the most profound and debated issues in modern physics, and it continues to captivate the minds of scientists and philosophers alike. The conflict between quantum superposition and classical observation presents a fundamental puzzle that has yet to be resolved. Numerous experimental approaches aim to shed light on this enigma. One such method involves exploring the boundaries of quantum behavior by creating larger and larger quantum superpositions, testing the limits of quantum mechanics in macroscopic systems. Another promising avenue of research focuses on ultra-precise measurements of quantum systems, attempting to catch the precise moment when the wave function collapses. With the rise of quantum computers and highly sensitive detectors, these experiments are reaching new levels of precision, providing hope that we may soon unlock the deeper mysteries of the quantum world. The measurement problem in quantum mechanics presents one of the most perplexing challenges in the realm of modern physics, with the very nature of the issue creating a cyclical conundrum. The act of measurement itself seems to be deeply entangled with the problem, raising questions that seem to lead back upon themselves. This circular dilemma leaves scientists pondering whether a full resolution of the measurement problem might necessitate a revolutionary shift in how we understand not only quantum mechanics, but also consciousness itself, our ability to observe and interpret the world. As experimental advancements continue to chip away at the unknowns, a definitive answer remains frustratingly elusive, propelling both rigorous scientific investigation and profound philosophical debate within the scientific community. The arrow of time, a concept deeply embedded in both the fabric of physics and the structure of our everyday experience, describes the apparent one-way flow of time from past to present and into the future. Unlike the spatial dimensions, where we are free to move back and forth, time appears to march in only one direction. This phenomenon is not merely an abstract concept. It is woven into the very core of physical laws and how we perceive the passage of life itself. We witness it in the simplest, most mundane occurrences. the warming of a cold drink, the fading of a once vibrant sunset, or the gradual deterioration of a neglected object over time. These processes unfold naturally in one direction, yet we never observe them spontaneously reversing themselves. The arrow of time is an inescapable reality that we must live with. At the heart of this directionality lies the second law of thermodynamics, a foundational principle of physics which dictates that the total entropy, essentially the measure of disorder or randomness in a system, must increase over time. This law provides a straightforward explanation for the arrow of time. It states that in an isolated system, entropy will always grow, meaning that things naturally evolve from more ordered states to more disordered ones. From the cooling of a hot cup of coffee to the crumbling of a sandcastle under the relentless push of the wind, these processes naturally progress toward disorder, never reversing on their own. This principle of increasing entropy gives rise to our perception of time's irreversible flow. Moreover, the arrow of time is tightly connected to the principle of causality, which holds that every effect must have a preceding cause. We observe events unfolding in a specific order, first the cause, then the effect. This sequential relationship between cause and effect reinforces our understanding of time as something that always moves forward, with the past serving as a precursor to the present and the present shaping the future. We experience this every day. We hear a sound before we see its source. We feel the impact of a falling object before we see it strike the ground. The sequence is undeniable, and this perceptual framework makes time seem as though it flows inevitably in one direction. Interestingly, though, most of the fundamental laws of physics are time-symmetric, meaning they work the same way whether time is running forward or backward. So, why then do we experience time flowing only in one direction? The answer lies in the initial conditions of our universe. The universe began in an incredibly ordered, low-entropy state, and as it has expanded and evolved, it has naturally moved toward higher entropy. This progression from order to disorder and the increasing entropy that comes with it shapes the directionality of time that we observe today. The second law of thermodynamics and the arrow of time are thus deeply intertwined, offering a glimpse into the underlying workings of the universe. Entropy, in the most basic sense, is a measure of disorder. It is the tendency for energy to disperse and spread out over time, like becoming less concentrated and less useful. Whether it's the disintegration of a stone in nature or the spread of heat from a hot object to a cooler one, entropy governs these processes. The principle that entropy must increase over time helps explain why we experience time as moving from past to future. The past, associated with lower entropy, is distinct from the future, which is marked by higher entropy. This one-way progression from low to high entropy gives time its apparent directionality. What if we were to encounter a region of space where entropy decreased? In such a scenario, we might perceive time as flowing backward. Yet, such a condition would violate the second law of thermodynamics as we understand it. This impossibility underscores the fundamental role that entropy plays in shaping our experience of time. The forward march of time, driven by the increase in entropy, seems to be an unavoidable reality of the universe. As we look outward to the cosmos, the relationship between entropy and time continues to guide our understanding of the universe's fate. The second law of thermodynamics predicts that the total entropy of an isolated system, like the entire universe, will continue to increase as the universe expands. Eventually, this might lead to a state referred to as heat death, where the universe reaches a state of maximum entropy, with all energy evenly spread out and no more useful work able to be done. This inevitability of entropy's increase serves as a reminder that the universe and everything within it is constantly changing. From the formation of stars to the eventual collapse of galaxies, entropy governs the very flow of existence, marking the universe's inexorable progression from order to disorder. Despite the apparent one-way flow of time, the question of whether time could ever reverse under certain circumstances remains an area of intense debate and speculation. In most instances, time seems to move forward, guided by the principles of the second law of thermodynamics. We age, a cup of coffee cools, and broken objects do not spontaneously reassemble. Yet, at the quantum level, the situation is more ambiguous. Some processes at this scale seem time-symmetric, meaning they could theoretically run backward or forward with equal ease. This paradox has led some physicists to speculate on the possibility of time reversal under certain extreme conditions. One such possibility comes from the idea that the universe's expansion might someday reverse. If the universe were to stop expanding and begin contracting, could this shift lead to a reversal of time's arrow? Another intriguing hypothesis arises from the study of black holes. Within these mysterious regions, where the laws of physics break down under immense gravitational forces, time might behave in ways that defy our traditional understanding. Some scientists have even proposed that time might run backward inside a black hole, though such speculations are, at present, entirely theoretical and unsupported by experimental evidence. In the realm of quantum mechanics, the behavior of particles and systems seems to conflict with our everyday experience of time. While the fundamental laws of physics that govern quantum particles are often time-symmetric, meaning they work equally well in both directions, we do not see this symmetry reflected in the larger-scale systems that make up our world. At the microscopic scale, particles may appear to behave in ways that defy the conventional one-way flow of time. But when these particles interact and combine in larger systems, the collective behavior leads to the emergence of time's direction. One of the key ideas that help reconcile this discrepancy is quantum decoherence. As quantum systems interact with their environment, they lose their quantum coherence, their ability to exist in multiple states simultaneously, and become more classical in nature. This process, which occurs incredibly rapidly for large objects, explains why we don't observe quantum phenomena in our daily lives. Quantum mechanics, in its pure form, may seem to lack a clear arrow of time, but once we account for the decoherence of quantum systems, we find that the second law of thermodynamics once again governs the behavior of larger systems, giving rise to the time asymmetry we observe. As scientists continue to explore the complex relationship between quantum mechanics and macroscopic time, the concept of causality remains central to our understanding of the universe. Causality, the principle that every effect has a cause, is deeply intertwined with the arrow of time. The sequence of events, cause followed by effect, is what defines our perception of time. A glass shatters when it falls, the shards never spontaneously reassemble. This one-way sequence reinforces our experience of time as something that moves forward, from past to present, and into the future. As our understanding of time evolves, scientists will continue to explore these mysteries, seeking a deeper insight into the true nature of time itself. The laws of physics, as we currently understand them, are often described as time-symmetric. This means they are as valid when moving forward in time as they are when moving backward. The processes at the core of these laws do not distinguish between past and future. This creates a puzzling contradiction. Why, if the fundamental laws of nature don't pick a direction, do we experience time as flowing in one direction? Why do we perceive the world as moving from the past to the future with an irreversible progression? This riddle is encapsulated in what is known as the arrow of time problem. The answer to this enigma, it turns out, is deeply rooted in the concept of entropy. In any closed system, entropy, which is a measure of disorder or randomness, tends to increase over time. This gradual increase in disorder gives time its arrow, providing a clear direction from the past to the future. It's as though time itself is marked by the steady march towards greater disorder. The second law of thermodynamics, which states that the entropy of an isolated system will always increase or remain the same, serves as a guiding principle for why we perceive time as moving only forward. As systems evolve, they move from states of lower entropy, more order, to states of higher entropy, greater disorder. It's this increase in entropy that allows us to differentiate between the past and the future. This relationship between the arrow of time and causality, where causes lead to effects, forms the foundation of our understanding of the universe. We can't, for example, unscramble an egg or reverse the flow of heat from a hot object to a cold one, because the increase in entropy prevents it. We remember the past, but not the future, because the universe is constantly transitioning toward higher entropy. This unidirectional flow of time is a fundamental aspect of how we experience reality. Yet this perception begins to unravel when we venture into the extreme environments around black holes. Near the singularity of a black hole, the point where the gravitational forces become infinitely strong, the nature of time itself starts to break down. The immense gravity warps space and time to such a degree that the distinction between past, present, and future begins to blur. In the vicinity of a black hole's singularity, space itself begins to curve so intensely that the conventional separation between time and space becomes less clear. Time, which we experience as a steady progression, could behave more like a spatial dimension with entirely unusual temporal effects. Some theories suggest that at the singularity, time might slow to an unimaginable crawl or even come to a complete halt. The familiar arrow of time, which points from the past to the future, might lose its direction altogether, and this could have profound implications for our understanding of cause and effect. In such a regime, the normal sequence of events, where one thing leads to another in a predictable order, might no longer apply. What would this mean for the very idea of causality? Could events unfold in a manner that seems chaotic or even paradoxical? At this point, the breakdown of conventional physics becomes apparent. Our current understanding of space, time, and causality is insufficient to describe what happens at the singularity of a black hole. To answer these questions fully, we need a theory of quantum gravity, something that combines the quantum realm, where particles behave in ways that defy classical physics, with the theory of general relativity, which governs massive objects like stars and black holes. Until such a theory is developed, the behavior of time near a black hole singularity remains one of the most compelling and mysterious questions in modern physics. One key idea that helps explain the arrow of time is the past hypothesis. This concept suggests that the early universe existed in a state of extremely low entropy or near perfect order. This low entropy state marks the starting point for the flow of time. If the universe began in a highly ordered state and over time has evolved towards greater disorder, this progression aligns perfectly with the second law of thermodynamics. The past hypothesis is essential for understanding why time flows in one direction, why we experience the present and remember the past, but not the future. This framework explains many everyday phenomena, why broken eggs cannot be unbroken, why heat always flows from hot to cold, and why we can recall what happened yesterday but cannot predict tomorrow with certainty. The universe's journey from low entropy to higher entropy is not just an abstract concept, it is woven into the fabric of our daily lives. However, the past hypothesis also raises more questions. Why was the early universe in such a low entropy state? Is this condition unique to our observable universe, or does it apply to the entire cosmos? These are questions that remain unresolved, and scientists continue to debate their implications. Nevertheless, the past hypothesis remains a cornerstone of our understanding of the arrow of time and its implications for the universe's evolution. The relationship between the arrow of time and free will is another area where these concepts become particularly fascinating. Time flows in one direction, and we experience this unidirectional flow in our daily lives as a series of cause and effect. Our brains process information in a way that creates a coherent narrative of our lives, reinforcing the sense that we are moving forward through time. This perception aligns with our feeling of agency. We make decisions and act on them with the expectation that our actions will shape the future. Yet, this sense of free will becomes more complicated when we consider the possibility that the universe is deterministic. If every future state is a result of past conditions, if the future is already written in the present, then our sense of making choices could be an illusion. This view suggests that our decisions are not truly free, but rather the inevitable outcome of a series of prior causes. On the other hand, quantum mechanics introduces an element of unpredictability into our understanding of the universe. In the quantum realm, particles behave probabilistically, meaning that exact outcomes cannot be predicted with certainty. Instead, there is a range of possible outcomes, each with a certain probability. This opens the door for the possibility of free will, as it allows for uncertainty and choice within the framework of physical laws. The interplay between quantum indeterminacy and the macroscopic arrow of time presents a fascinating paradox. While the arrow of time appears to guide us in one direction, quantum mechanics suggests that the future might not be as fixed as we once thought. This tension between determinism and free will is one of the most intriguing aspects of modern physics, and it continues to challenge our understanding of how the universe works. Time, as we experience it, is not uniform across the entire universe. According to Albert Einstein's theory of general relativity, the fabric of space-time can be warped by gravity. This means that time doesn't pass at the same rate everywhere. Its flow is affected by the presence of massive objects. The stronger the gravitational field, the more time is stretched. Near extremely massive objects like black holes, time slows down drastically. This phenomenon, known as gravitational time dilation, means that time passes much more slowly for an object close to a black hole compared to one that is farther away. This effect becomes particularly noticeable near a black hole's event horizon, the boundary beyond which not even light can escape. To an observer far from the black hole, it would appear as though time near the event horizon is nearly frozen. Interestingly, time dilation isn't just something that occurs near black holes. Even on Earth, we experience tiny differences in the passage of time depending on our location. Clocks at sea level, where the gravitational pull is slightly stronger, tick more slowly than those located on mountaintops, where gravity is weaker. This effect is so subtle that we don't notice it in our daily lives, but it must be accounted for in technologies like GPS, where even small discrepancies in time can lead to significant errors in location. On a cosmic scale, the expansion of the universe also affects time. In the early universe, time moved more slowly relative to today. As space has expanded, the passage of time has changed, influencing how light travels and how we perceive distant objects. When we observe galaxies that are billions of light years away, we are not just looking at them in space, but also looking back in time, seeing them as they were when the universe was much younger, and time itself flowed differently. Consciousness, the experience of being aware of oneself and the world, remains one of the most profound mysteries of human existence. Despite its central role in shaping our reality, consciousness resists easy definition or measurement. Unlike physical phenomena, consciousness is inherently subjective. We can observe and measure brain activity, but we cannot directly quantify the internal personal experience of awareness. This makes consciousness particularly challenging to study scientifically. Moreover, the phenomenon of consciousness encompasses a wide range of experiences, from basic awareness to complex self-reflection and decision-making. This diversity adds another layer of complexity to the task of understanding and defining consciousness. While we are beginning to gain insights into the brain's workings, the full nature of consciousness remains elusive, and its relationship to time, perception, and reality continues to be a topic of intense philosophical and scientific debate. The relationship between brain activity and conscious experience remains one of the most perplexing and enigmatic challenges in both neuroscience and philosophy. Despite the immense strides made in understanding the brain's complex functions, the precise nature of how subjective consciousness emerges from neural processes is still poorly understood. This mystery not only complicates efforts to define consciousness in purely physical terms, but also pushes the boundaries of what we know about the mind, cognition, and even reality itself. In the face of these challenges, scientists continue to explore consciousness from multiple angles. Neuroscientists, psychologists, and philosophers all aim to untangle this web of complexity. As technology advances and our understanding of the brain's inner workings deepens, the hope is that we will gradually uncover the mechanisms behind consciousness and refine our scientific definitions and explanations of this fundamental aspect of human existence. Yet, despite our expanding knowledge, the question of how consciousness emerges from the physical brain remains one of the most profound, unsolved riddles in both fields. The current state of scientific research reveals that while we have made significant progress in understanding the brain's functions, the exact processes that give rise to conscious experience remain hotly debated. What we do know is that consciousness is thought to arise from the intricate interactions of billions of neurons within our brains. These neurons form elaborate networks that communicate through electrical and chemical signals, coordinating complex activities that underpin our thoughts, perceptions, and actions. Some theories suggest that consciousness emerges when these neural networks reach a certain level of complexity and integration. At this stage, the brain becomes capable of processing and synthesizing vast amounts of information. A leading idea called the Integrated Information Theory, IIT, proposes that consciousness correlates with the quality and quantity of information integrated by the brain. According to this theory, consciousness is not simply the sum of individual neural activities, but a unified process that brings together sensory inputs, memories, and internal states into a coherent model of reality. Although researchers have identified certain regions of the brain, such as the prefrontal cortex and thalamus, that seem to be involved in conscious experience, the exact neural correlates of consciousness remain elusive. The deeper we delve into these questions, the more complex the landscape becomes. While advancements in neuroimaging and brain mapping technologies have provided invaluable insights into brain structure and function, the challenge of linking specific neural activity to the rich, subjective experience of consciousness remains a formidable hurdle. At the heart of this challenge lies what has been called the hard problem of consciousness, a term coined by philosopher David Chalmers to describe the difficulty in explaining how and why we have subjective, conscious experiences. While we can observe brain activity and behavior, and even describe neural pathways and cognitive processes, the question of why these processes give rise to the rich inner world of thoughts, emotions, and sensations remains unanswered. This is where the hard problem diverges from what are often referred to as the easy problems of consciousness, those that focus on understanding cognitive functions such as memory, perception, and decision-making. The hard problem takes us into the realm of qualitative experience, or qualia, the unique individual nature of what it feels like to be a conscious being. For example, we can explain how the brain processes visual stimuli, such as light hitting the retina and being translated into neural signals. However, this explanation does little to illuminate why we experience the sensation of seeing colors or shapes. In essence, the hard problem asks why there is something it feels like to experience the world. It seeks to understand how physical processes in the brain give rise to the personal, internal experience of being aware. To add to the complexity, various perspectives have been proposed to solve this mystery. Some take a materialist view, suggesting that consciousness can and should be explained purely in physical terms, perhaps emerging from the interaction of neurons in ways we have yet to fully understand. Others, however, argue for dualism, the idea that consciousness may exist independently of the brain and might even be a fundamental property of the universe rather than simply a byproduct of neural activity. Despite decades of research, the hard problem of consciousness continues to baffle scientists and philosophers alike. This ongoing mystery sits at the intersection of several disciplines, including neuroscience, psychology, and metaphysics. One of the more controversial and intriguing proposals is the idea that consciousness is a fundamental aspect of reality itself, much like mass or electric charge. This perspective, known as panpsychism, suggests that all matter may possess some degree of consciousness or subjective experience. Proponents of this view argue that it could help address the hard problem by offering a framework in which consciousness is intrinsic to the fabric of the universe and not merely a product of biological processes. According to panpsychism, if consciousness is a fundamental feature of reality, it could be easier to understand how complex forms of awareness arise from simpler forms of matter, such as the neurons in our brains. Critics, however, remain skeptical, pointing out that there is currently no empirical evidence to support this idea. They argue that our understanding of consciousness is closely tied to brain activity and biological processes, making it difficult to imagine consciousness as existing independently of these structures. The idea that consciousness is an intrinsic property of the universe is still speculative, but it continues to spark research and debate in areas such as quantum physics, neuroscience, and the philosophy of mind. As our understanding of both the universe and consciousness evolves, new insights may emerge that provide a more complete picture of this tantalizing possibility. One particularly intriguing area of research involves the potential connection between quantum mechanics and consciousness. Some scientists have hypothesized that quantum processes in the brain may play a role in generating conscious experiences. The theory known as quantum consciousness suggests that quantum effects within neural microtubules, tiny structures within neurons, could be responsible for creating our subjective awareness. Proponents of this hypothesis argue that quantum phenomena, such as superposition, could enable the brain to perform a form of information processing that goes beyond classical computation. This might help explain the complex and seemingly non-deterministic nature of human thought and decision-making. However, critics of this theory point out that the brain is too warm and wet for quantum effects to persist long enough to have a significant influence on cognition. Quantum phenomena typically occur at subatomic scales and extremely low temperatures, conditions that are not found in biological systems. This raises serious questions about the feasibility of quantum consciousness as an explanation for subjective awareness. The relationship between quantum mechanics and consciousness remains a topic of intense debate and exploration. As researchers continue to investigate the brain, the nature of consciousness, and their potential links to quantum phenomena, we may one day unlock new dimensions of understanding about the mind, the universe, and the very nature of existence itself. Yet, for now, the enigma of how conscious experience arises from the physical brain remains one of the most profound and captivating mysteries in science and philosophy. However, recent breakthroughs in the study of quantum processes in photosynthesis and bird navigation have ignited renewed discussions on a topic that has long remained on the fringes of scientific inquiry: the connection between quantum mechanics and consciousness. While the precise link between the two remains speculative, the exploration of these potential connections is opening new doors that could radically expand our understanding of both the microscopic world of quantum physics and the complex workings of the human mind. As we delve deeper into the quantum realm and probe the intricacies of consciousness, we may find ourselves uncovering profound insights into the very nature of reality and our place within it. At the heart of this quest is the global workspace theory of consciousness, a concept that has gained traction in the realm of neuroscience and cognitive science. This theory proposes that conscious awareness emerges from a central exchange of information within the brain. Essentially, different areas of the brain compete to broadcast their information to a shared mental workspace. When information manages to access this workspace, it becomes simultaneously available to multiple brain regions, effectively creating the conscious experience that we are familiar with. Picture the brain as a bustling office building, with numerous departments all working on different tasks. The global workspace functions much like a central bulletin board, where important messages are posted for everyone to see. When a department has crucial information, it competes to pin its message on this board. Once the message is posted, it is available to all departments, just as conscious thoughts become available to various mental processes across the brain. This dynamic helps explain why we can only focus on a limited amount of information at a time. Just as a bulletin board has finite space, our conscious awareness can only hold so much information before it becomes overwhelmed. The global workspace theory also provides an explanation for why unconscious processes can suddenly emerge into our conscious awareness when they are deemed important enough to access the workspace. Neuroscientific research has provided strong evidence for this theory, with brain activity patterns observed when information transitions into conscious awareness. These patterns show that when information enters the global workspace, it activates widespread areas of the brain simultaneously, consistent with the idea of a global broadcast. This model continues to shape our understanding of how the brain generates the subjective experience of consciousness. Altered states of consciousness, whether they arise naturally or through external influences, offer another rich source of insight into the nature of awareness and the complexity of human perception. One of the most fascinating of these altered states is dreaming. During sleep, our brains generate vivid, sometimes surreal experiences that feel incredibly real, despite being disconnected from external sensory input. This phenomenon challenges our conventional understanding of how consciousness arises and suggests that the brain has the capacity to produce conscious experiences independent of external stimuli. Meditation and mindfulness practices also induce altered states of consciousness, providing practitioners with the opportunity to observe their thoughts, sensations, and emotions with a detached sense of awareness. These experiences imply that consciousness is not a static state, but rather something that can be trained, expanded, and refined. Through consistent practice, individuals can enhance their ability to focus, regulate their emotions, and gain deeper insight into the workings of their own minds. This suggests that the potential to shape our conscious experience may lie not only in understanding the brain, but also in harnessing the mind's capacity for introspection and self-regulation. The use of psychedelic substances has also garnered attention for its ability to induce profound alterations in perception, cognition, and self-awareness. Studies on these altered states have led to new theories about the role of specific brain networks in shaping our conscious experience. Additionally, the exploration of these states has inspired new approaches to mental health, including potential treatments for conditions such as depression, anxiety, and PTSD. The insights gained from these research areas are beginning to reshape our understanding of consciousness, highlighting its complexity and the ways in which external factors can influence its expression. One of the most profound and contentious questions in contemporary science concerns the potential for artificial intelligence, AI, to achieve true consciousness. This question touches upon fundamental issues in philosophy, neuroscience, and computer science, and it remains one of the most debated topics in modern research. At present, even the most advanced AI systems are not conscious in the way humans are. While AI can process vast amounts of information and perform tasks with impressive speed and accuracy, it lacks subjective experiences, self-awareness, and the capacity for introspection. Yet some scientists argue that as AI technology continues to evolve, it may eventually develop qualities that we associate with consciousness. One perspective is that consciousness could emerge from the processing of complex information, suggesting that theoretically, a sufficiently advanced AI might achieve a form of awareness. On the other hand, critics of this view contend that biological brains possess unique properties, such as their intricate biochemical processes that machines may never be able to replicate. As a result, the notion of artificial consciousness remains highly speculative and riddled with uncertainty. The possibility of creating truly conscious AI raises profound ethical dilemmas. If AI were to develop self-awareness, what rights and moral considerations would apply to such entities? Would they deserve the same ethical protections as humans? These questions have yet to be answered, and for now, the issue remains speculative. Nonetheless, as AI technology advances and we gain a deeper understanding of both artificial and biological systems, this question will likely become increasingly relevant, prompting us to reconsider what it means to be conscious. The relationship between free will and consciousness is another deeply complex and often debated topic in philosophy, neuroscience, and psychology. Consciousness, our subjective awareness of ourselves and the world around us, appears to be intimately connected to our sense of free will, the idea that we have the ability to make decisions that are not entirely determined by external forces. Many argue that consciousness is a prerequisite for free will. Without awareness of our thoughts and actions, it would be difficult to claim that we are making truly autonomous choices. Our conscious experience allows us to deliberate, consider different alternatives, and ultimately make decisions based on our reasoning and desires. However, some scientific studies have challenged this view, suggesting that our brains may make decisions before we become consciously aware of them. This finding raises questions about the causal relationship between our conscious thoughts and the actions that follow. Are our conscious thoughts the origin of our actions, or are they simply a rationalization of decisions that have already been made? Some critics of the concept of free will argue that our choices are ultimately determined by prior causes, such as our genetics, upbringing, and the circumstances we find ourselves in. According to this view, free will is an illusion, and our conscious experience is merely a byproduct of deterministic processes. Despite these challenges, many researchers and philosophers continue to argue that consciousness and free will are deeply intertwined. They maintain that our ability to reflect on our choices and modify our behavior over time constitutes a form of free will, even if it is not absolute or unconstrained. This ongoing debate has significant implications for how we understand moral responsibility, the legal system, and human agency. It also raises fundamental questions about the nature of consciousness itself and whether we are truly in control of our thoughts and actions. In the end, consciousness remains one of the greatest mysteries in science, and unraveling its secrets could fundamentally alter our understanding of reality. As we probe deeper into the nature of consciousness, we may find that our subjective experiences are far more than just byproducts of brain activity. They could, in fact, be intimately linked to the very fabric of the universe itself. Recent theories in quantum physics suggest that consciousness might play a fundamental role in shaping reality at its most basic level. If these theories prove correct, it would mean that our thoughts and perceptions are not merely passive observers of the world, but active participants in its creation. Such a view challenges the traditional understanding of an objective, independent reality and offers the tantalizing possibility that consciousness may be far more powerful and far more integrated into the fabric of existence than we ever imagined. As our understanding of consciousness deepens, it holds the potential to completely transform the way we approach artificial intelligence. Imagine, for a moment, that we could pinpoint the exact components that give rise to subjective experience, the essence of being aware, the sense of I that defines our consciousness. If we could unravel this mystery, we might be able to create machines that aren't just intelligent, but sentient, machines that can experience the world in the same way that we do. This would blur the line between biological and artificial consciousness, forcing us to fundamentally reconsider what it means to be aware, to think, to live. It could redefine what it means to be alive itself. This prospect is not merely theoretical. There is a growing body of scientific and philosophical inquiry into the nature of consciousness, one that could, in time, extend beyond human cognition to encompass the universe as a whole. This idea, known as panpsychism, is gradually gaining traction among a select group of thinkers. Panpsychism suggests that consciousness could be a fundamental feature of the universe, woven into the very fabric of reality. If this theory is true, consciousness wouldn't be confined to humans, animals, or even plants. It would be as integral to the cosmos as space and time themselves. Such a revelation would force us to rethink not only the nature of life, but the universe itself, challenging our assumptions about the very ground we stand on and the forces that govern existence. Linked to these ideas is the anthropic principle, a captivating concept in cosmology that offers an explanation for why our universe appears to be uniquely suited for the existence of life, particularly life like ours. At its core, the anthropic principle offers an intriguing perspective on the fine-tuning of the universe. It suggests that our observations of the cosmos are not neutral. They are inherently biased by the fact that we are conscious observers. In other words, the very fact that we exist to ask these questions influences the answers we seek. This principle, in both its weak and strong forms, pushes us to consider whether the universe was designed or whether we simply find ourselves in a reality that happens to have the right conditions for life. The weak anthropic principle is often seen as more scientifically grounded. It simply acknowledges that we can only observe a universe that supports our existence. It doesn't delve into questions of purpose or inevitability. It merely describes the constraints imposed by our own existence. The strong anthropic principle, by contrast, suggests a cosmic purpose or necessity behind the emergence of life, a notion that often overlaps with theological or philosophical arguments about the meaning of existence. As these theories continue to evolve, they challenge us to expand our thinking. Could it be that the universe is not only fine-tuned for life, but that life is an essential part of the universe's deeper, intrinsic nature? What if consciousness itself is not just a product of biology, but a universal property of the cosmos, stretching far beyond the boundaries of our own understanding? In the end, the anthropic principle and the concept of the multiverse open up a fascinating realm of possibilities. Whether we're talking about the fine-tuning of the universe, the rise of artificial consciousness, or the potential for conscious awareness throughout the cosmos, these ideas challenge us to rethink the fundamental nature of existence and perhaps to discover that the universe is far more mysterious and interconnected than we could ever imagine. The anthropic principle, a concept deeply embedded in cosmology, is often seen as a crucial framework for understanding the unique conditions of our universe. Proponents of the principle argue that it provides an invaluable lens through which we can comprehend our place in the cosmos, particularly when faced with the seemingly improbable circumstances required for life to flourish. It suggests that of all the possible universes that could exist, we find ourselves in one that just so happens to be capable of sustaining life. This doesn't answer the underlying question of why these conditions exist, but it offers an intriguing model for understanding why we observe a universe that appears so fine-tuned for life. Rather than invoking notions of purpose or intelligent design, the anthropic principle presents an alternative narrative, that the universe must be as it is simply because we are here to observe it. However, this principle has sparked significant debate and controversy, engaging both scientists and philosophers in discussions about the nature of existence and the apparent order of the universe. At the heart of this debate lies the observation that the laws and constants of nature seem so precisely calibrated to allow life to exist. This realization leads to profound questions about the nature of our cosmos, inviting various interpretations, some more metaphysical than others. For many who hold religious views, the anthropic principle can be seen as evidence supporting the idea of purposeful creation. The argument follows that the specific and precise conditions required for life are not a random occurrence, but instead point to a deliberate act of creation by a divine creator. The anthropic principle, in this view, serves as scientific confirmation that the universe was designed with life in mind, aligning with many theistic beliefs. In this sense, the universe becomes a stage crafted intentionally for conscious beings to arise. On the other hand, secular philosophers and many scientists interpret the anthropic principle from a more naturalistic standpoint. Instead of invoking divine intent, they suggest that our universe may simply be one among an enormous number of potential universes, an idea that leads to the concept of a multiverse. According to this perspective, the apparent fine-tuning we observe is merely a consequence of cosmic natural selection. We are here because we inhabit a universe capable of supporting life, while countless other universes with different physical laws and constants simply remain unobserved because they cannot support life. In this view, the anthropic principle offers no deeper explanation for the fine-tuning of the universe, but rather provides a way to frame our observations without resorting to metaphysical or theological explanations. The debate surrounding the anthropic principle is more than just an academic exercise. It touches on the very essence of human existence and our understanding of the universe. It challenges us to consider whether there is a deeper meaning behind the laws of nature, or if they are simply the result of random processes and statistical likelihoods. It also forces us to question how we define life itself. Could life exist in forms radically different from the carbon-based organisms we know? The search for extraterrestrial life, for example, is in many ways influenced by the anthropic principle. It encourages us to explore environments where life, as we understand it, might arise, such as planets with liquid water, stable atmospheres, and moderate temperatures. However, it also challenges this Earth-centric view by reminding us that life could exist in forms we cannot yet imagine, expanding our search to more extreme environments such as the methane lakes of Titan or the subsurface oceans of moons like Europa. While some see the anthropic principle as a necessary guide for navigating the search for life elsewhere, others view it with skepticism. Critics argue that it can lead to what they call lazy thinking, as it sometimes serves as a convenient explanation for cosmic coincidences without further investigation. Rather than pushing the boundaries of scientific inquiry, the principle, they argue, can stop us from seeking deeper explanations for the apparent fine-tuning of the universe. This criticism is particularly pertinent when the anthropic principle is invoked in the context of multiverse theories, where the existence of countless universes, each with different constants, is used to explain the apparent fine-tuning. The problem here, according to critics, is that these universes are, by definition, unobservable, which makes it impossible to test or falsify these ideas through direct evidence. The anthropic principle also faces criticism for being unfalsifiable. In scientific methodology, a theory must be testable in order to be considered valid. But the anthropic principle relies on the assumption that we're in a universe that can support life. Because we cannot observe other universes that might not support life, the principle remains, to some, an untestable proposition. This presents a significant challenge to its scientific merit. Without the possibility of empirical testing, it becomes difficult to evaluate the principle's validity or use it as a foundation for further scientific exploration. One area where the anthropic principle intersects with current scientific inquiry is in the search for extraterrestrial life. The concept that the universe must have certain properties to support conscious life has profound implications for astrobiology. It invites scientists to focus on planets and moons with conditions that mirror Earth's, what we call the Goldilocks zone, the region around a star where the temperature is just right for liquid water to exist on the surface of a planet. Earth sits comfortably within this zone, whereas Venus, too close to the Sun, and Mars, too far, both fail to meet the necessary conditions for liquid water to persist. In our solar system, this precise positioning is what has allowed Earth to maintain the delicate balance needed for life to thrive. The Goldilocks zone, which is central to our search for habitable exoplanets, illustrates the concept of the anthropic principle on a smaller, more tangible scale. If Earth exists in the perfect zone with just the right conditions for life, then it seems to echo the fine-tuning that the anthropic principle suggests. The existence of such a zone implies that the universe is, in some sense, made to support life. But the anthropic principle does not seek to explain why these conditions exist. It simply states that they must exist for us to be here to observe them. The universe may be as it is simply because, in a universe with different laws, life as we know it could not exist, and we, therefore, could not exist to ask these questions. Despite its challenges and criticisms, the anthropic principle remains a crucial element in cosmological discussions. As both a scientific and philosophical concept, it draws us into deeper inquiries about the nature of reality, the role of conscious observers, and the possibility of other universes. In the end, it asks the most fundamental question: why is the universe as it is, and what does it mean for our place within it? To explore these questions further, scientists have turned to computer simulations, which allow them to model different universes by adjusting fundamental constants and laws of physics. These simulations help illustrate the vast array of possibilities for what a universe might look like under different conditions. Could other universes, governed by different laws, host intelligent life? If so, how might they differ from our own? While these simulations cannot provide definitive answers, they offer a way to explore the vast range of conditions under which life could exist, even if those universes remain beyond our observational reach. Another avenue of investigation into the anthropic principle comes from the study of multiverse theories. If our universe is just one among many, each with different laws, then perhaps evidence for this idea might one day emerge. Such evidence could come from cosmological observations or advances in quantum mechanics, which might offer insights into the nature of multiple universes. However, these ideas remain speculative and untestable, making them difficult to incorporate into a rigorous scientific framework. Yet, they provide an intriguing backdrop for discussions about the nature of reality and our place within it. Lastly, one potential way to challenge the anthropic principle is to search for life in environments vastly different from those we typically associate with habitability. If life can exist in extreme conditions on Earth, such as in deep-sea vents or in acidic environments, then it stands to reason that life could exist in places previously thought to be inhospitable. Such discoveries would force us to rethink the parameters we use to define life and challenge the assumptions underlying the anthropic principle. Thus, the anthropic principle remains a central topic in our search for understanding, offering both guidance and challenge as we explore the vast and mysterious cosmos. However, this idea does not completely negate the principle. Rather, it serves to broaden our understanding of the myriad conditions that could support life. The holographic principle, a revolutionary concept in theoretical physics, suggests that our perception of reality could be entirely wrong. It proposes that the universe as we know it, our three-dimensional reality, might not be what it seems at all. Instead, it could be an illusion, a projection emerging from a distant, two-dimensional surface. To grasp this radical idea, let us take a moment to imagine the cosmos as a vast hologram. A hologram that, despite appearing to possess depth and volume, is fundamentally flat. Much like how a 2D hologram can create the illusion of three-dimensional objects, the holographic principle suggests that the fabric of our universe, time and space, gravity and matter, could all emerge from information encoded on a boundary, not in the familiar 3D space we experience. This theory was sparked by studies of black holes, where physicists noticed that all the information about objects falling into black holes appears to be stored on the event horizon, the two-dimensional boundary surrounding them. This startling discovery led to the hypothesis that perhaps the entire universe operates in a similar fashion. At first glance, this concept might seem fantastical, almost impossible to grasp. After all, we experience the universe in three dimensions, where gravity bends space and time, and our lives unfold in a continuous flow of events. Yet, the holographic principle challenges all of this, proposing that gravity, which governs the largest structures in the cosmos, might not be a fundamental force at all. Instead, it could be an emergent phenomenon arising from more basic quantum processes occurring on a lower dimensional surface. This insight continues to captivate physicists who are trying to reconcile the strange world of quantum mechanics with the vastness of gravitational theory. In practical terms, the holographic principle suggests that our entire universe, everything from galaxies and stars to black holes and quantum fields, might ultimately be a projection. Just as a hologram on a flat surface can appear three-dimensional, the universe could be a reflection of data encoded on a two-dimensional boundary, far beyond the reaches of our current observational tools. This boundary could be the edge of the observable universe, acting as a kind of cosmic hard drive, storing all the information about the cosmos within its flat surface. In essence, what we perceive as depth, volume, and the very fabric of space-time may be nothing more than an illusion created from this stored data. The ramifications of such a theory are immense. It would revolutionize our understanding of space-time and the nature of reality itself. Not only would it challenge the assumptions of how space and time function, but it would also reframe our very notions of what it means to exist. It pushes us to rethink everything we thought we knew about the universe, suggesting that perhaps we live inside a vast, interconnected web of information, with the physical world we experience being merely a shadow of a much deeper reality. This is the essence of the holographic principle. One of the most compelling pieces of evidence for this radical theory comes from the study of black holes. Physicists discovered that the entropy of a black hole, essentially the amount of information it contains, is proportional to the surface area of its event horizon, not its volume. This was a surprising revelation because, in most cases, the more massive an object, the more information it should contain. But in the case of black holes, it's the surface area, the boundary, that determines the amount of information, lending weight to the holographic idea that space itself may be described by data on a two-dimensional surface. String theory, a major contender for the unification of all the forces of nature, also lends support to the holographic principle. According to string theory, the basic constituents of matter are not point-like particles, as traditionally thought, but rather tiny, vibrating strings of energy. These strings exist in multiple dimensions, beyond the familiar four we experience in daily life, potentially up to 11 dimensions. String theory proposes that these higher dimensional strings can be understood in terms of quantum field theories that operate on lower dimensional surfaces. This idea, known as the ADS-CFT correspondence, shows that certain gravitational theories in higher dimensional spaces are mathematically equivalent to quantum field theories on their boundaries, providing a concrete realization of the holographic principle within string theory. In addition, quantum entanglement, one of the most mysterious phenomena in quantum mechanics, also ties into the holographic principle. Research has revealed that the entanglement entropy of a region in quantum field theory, which measures how much quantum information is shared between distant parts of the universe, is related to the area of the boundary of that region. This mirrors the behavior predicted by the holographic principle, where information is encoded on the boundary of a space rather than within the space itself. This deep connection between quantum information and geometry further strengthens the argument for the holographic model. While these various lines of evidence are compelling, it's important to acknowledge that the holographic principle remains a theoretical concept. Much work remains to be done before we can definitively prove or disprove it. However, the principle's potential to unify quantum mechanics and gravity, the two pillars of modern physics that have yet to be reconciled, makes it a crucial area of study. As scientists delve deeper into the mysteries of the cosmos, this theory might unlock the answers to some of the most fundamental questions about the universe. The intersection between the holographic principle and string theory is one of the most exciting areas of theoretical physics. String theory, which posits that all particles are made of vibrating strings, provides a framework for understanding the fundamental forces of nature. In certain string theory models, there is a correspondence between gravitational theories in higher dimensional spaces and quantum field theories on the boundaries of those spaces. This connection, known as the ADS-CFT correspondence, offers a direct realization of the holographic principle. Through this relationship, string theory can help solve complex problems in quantum field theory, and vice versa, leading to new insights in both fields. Moreover, this correspondence suggests that our universe might not be the solid, three-dimensional reality we experience, but rather a projection of information encoded on a two-dimensional boundary. If proven true, this concept would upend everything we know about space and time, offering a new, deeper understanding of the cosmos. It could explain phenomena like black holes and quantum gravity, while also unifying the diverse theories of physics into a single framework. The holographic principle forces us to reconsider our understanding of reality itself. It suggests that the universe is not a solid, three-dimensional object, but rather a vast, intricate projection. This idea compels us to reevaluate how we think about space, time, and the very fabric of the cosmos. If the universe is indeed a hologram with information stored on a boundary far beyond our reach, it raises profound questions about the nature of existence. Could everything we see, touch, and experience simply be a projection of information from a distant surface? One of the most profound implications of the holographic principle is its potential resolution of the black hole information paradox. For years, physicists have struggled with the question of what happens to the information contained in objects that fall into a black hole. If information is lost inside a black hole, it would violate the fundamental principles of quantum mechanics. The holographic principle offers a solution. It suggests that this information is not lost, but encoded on the event horizon of the black hole, preserved in two-dimensional form. This insight could resolve one of the most perplexing puzzles in modern physics, offering a way to reconcile the strange behavior of black holes with the laws of quantum mechanics. In the end, the holographic principle opens up new avenues for exploration. It invites us to question our most basic assumptions about the universe and offers the possibility that the reality we experience may be far more complex and mysterious than we ever imagined. As research into this theory continues, it could lead to groundbreaking discoveries that change our understanding of the cosmos, pushing the boundaries of human knowledge to new, unimaginable heights. The holographic principle is not just a scientific theory, it is a gateway to a new way of seeing the universe. The holographic principle presents an intriguing and potentially groundbreaking solution to some of the most persistent questions in physics, especially in reconciling quantum mechanics with gravity, a task that has long remained one of the greatest challenges for physicists. The idea itself offers an elegant way of simplifying the vast complexities that arise when attempting to unify these two foundational theories of nature. By reducing the number of dimensions needed to describe the universe, the holographic principle makes the mathematical framework required for this unification less complicated and more tractable. But beyond simplifying mathematical models, the holographic principle fundamentally reshapes our understanding of space and time. It suggests that the three-dimensional reality we experience might not be as it seems. Instead, it could be a projection, a shadow of a much more fundamental two-dimensional surface. This startling idea has the potential to resolve some of the major inconsistencies in our understanding of cosmic inflation, the very early stages of the universe, and the nature of reality itself. From the smallest quantum scales to the vastness of the cosmos, the holographic principle could offer a unified framework that connects them all, offering a more coherent picture of the universe. At the heart of this exploration lies a theoretical concept known as the AD-S-CFT correspondence, or the anti-de Sitter conformal field theory correspondence. This groundbreaking idea proposes a deep, previously unsuspected relationship between two seemingly disparate fields of study. On one hand, we have a theory of gravity operating in a space known as anti-de Sitter, AD-S space, which is a model of negatively curved, warped spacetime. On the other hand, we have a quantum field theory which describes particles and forces without involving gravity functioning on the boundary of this warped space. The AD-S-CFT correspondence suggests that, despite appearing to be fundamentally different, these two theories are in fact equivalent descriptions of the same physical reality. In essence, it's as if we have two separate languages describing the same phenomenon, each with its own strengths and computational advantages. This correspondence provides a concrete bridge between gravity and quantum mechanics, suggesting that these seemingly incompatible forces could in fact be part of a larger unified framework. The AD-S-CFT correspondence is intimately tied to the holographic principle. Proposed by physicists Gerard Hooft and Leonard Susskind, the holographic principle asserts that all the information contained within a given volume of space can be described by a theory that operates solely on the boundary of that space. This concept is similar to the way a hologram works, where a three-dimensional image is encoded on a two-dimensional surface. In the context of AD-S-CFT, this means that the gravitational theory that operates in the bulk of AD-S space can be viewed as equivalent to a non-gravitational theory on the boundary of that space. The implications of this are profound, offering new perspectives on quantum gravity, black holes, and the very nature of space-time itself. The holographic principle provides a framework that allows us to consider the possibility that the universe we see around us, our three-dimensional reality, is nothing more than a projection of information encoded on a lower dimensional surface. This radical shift in how we view the cosmos holds the potential to solve some of the most difficult puzzles in modern physics, such as the black hole information paradox. The holographic principle also offers a new perspective on quantum entanglement, one of the most enigmatic phenomena in quantum mechanics. Quantum entanglement describes the situation in which two or more particles become deeply correlated in such a way that the quantum state of one particle cannot be described independently of the others, even when they are separated by vast distances. Einstein famously referred to this as spooky action at a distance. And for many years, it seemed to challenge our classical understanding of how information and influence can travel through space-time. Some physicists have suggested that the holographic principle may provide an explanation for quantum entanglement. They hypothesized that the correlations between entangled particles could be understood as projections of information encoded on a lower dimensional surface, as described by the holographic principle. In this view, the spooky action at a distance might not be so spooky after all. Instead, it could be a manifestation of a deeper, more fundamental reality where the particles are simply different projections of the same underlying information. This idea extends to our understanding of black holes, which have long been one of the most mysterious objects in the universe. According to the holographic principle, all the information contained within a black hole, everything inside its event horizon, could be encoded on its boundary, its event horizon. This radical suggestion challenges the conventional wisdom that information is lost forever when it crosses the event horizon of a black hole. Instead, the holographic principle implies that this information is not lost, but preserved on the surface of the black hole. Such a perspective offers a potential solution to the black hole information paradox, which has puzzled physicists for decades. If information is indeed preserved in this way, it could align with the principles of quantum mechanics, where information is never truly destroyed, while also satisfying the requirements of general relativity, which governs the behavior of black holes. This breakthrough could help bridge the gap between these two fundamental theories of physics, providing new tools for tackling the most challenging questions in the field. The holographic principle also has profound implications for the study of black hole entropy and Hawking radiation. According to the principle, the entropy of a black hole, essentially the measure of its information content, is proportional not to its volume, as one might expect, but to its surface area. This realization has led to new insights into how information can be released from black holes through the process of Hawking radiation, thus maintaining consistency with the principles of quantum mechanics while still aligning with the predictions of general relativity. Despite its promise, testing the holographic principle is no simple task. The vast scales involved and the extreme conditions that need to be replicated make it a formidable challenge for experimental physicists. Nonetheless, researchers have proposed several creative approaches to test this theory. One potential method involves studying the cosmic microwave background radiation, essentially the oldest light in the universe. By analyzing tiny fluctuations in this radiation, scientists hope to detect correlations that could indicate the presence of a holographic structure underlying the universe. These correlations would suggest that the three-dimensional space we observe is in fact a projection from a two-dimensional surface. Another avenue of investigation focuses on quantum entanglement in the vicinity of black holes. According to the holographic principle, the information contained within a black hole should be proportional to its surface area, not its volume. By examining the behavior of entangled particles near the event horizon of a black hole, scientists hope to uncover evidence supporting this relationship, further strengthening the case for the holographic nature of reality. Additionally, physicists are exploring the possibility of creating laboratory experiments that mimic the holographic principle. By using ultra-cold atoms or specially engineered materials, researchers aim to replicate some of the conditions predicted by the holographic theory, albeit on a much smaller, more manageable scale. While these analog experiments may not directly prove the validity of the cosmic holography, they could offer valuable insights into the underlying principles that govern our universe. As we contemplate the future of the universe, it is impossible not to consider the possible fates that await us. Current theories suggest a number of potential scenarios, each more astonishing than the last. One such theory is the Big Freeze, in which the universe continues to expand indefinitely. In this future, stars burn out, galaxies grow dark, and the cosmos becomes an ever-growing void. The universe would grow colder, and emptier as time stretches on, eventually reaching a state of maximum entropy where no further work or energy exchange is possible. This fate, while still a subject of much debate, represents one of the most widely accepted possibilities based on our current understanding of cosmology and the accelerating expansion of space. Alternatively, the Big Crunch presents a more dramatic ending, one in which the universe's expansion slows down and eventually reverses. Gravity would overpower the force of cosmic expansion, pulling all matter back together into a dense, highly concentrated singularity. This collapse could mirror the conditions that existed before the Big Bang, potentially giving rise to a new universe in a cycle of cosmic rebirth, a concept referred to as the Big Bounce. The ultimate fate of the universe, then, might not be an end but a transformation, a cyclical process that could repeat ad infinitum. On the other hand, the Big Rip suggests a far more violent and cataclysmic end. This scenario involves the mysterious force of dark energy growing so strong that it tears apart the very fabric of space-time. Galaxies, stars, planets, and even atoms would be ripped apart by this force, reducing everything in the universe to its most fundamental components. In this terrifying future, the universe would disintegrate at the most fundamental level, and all structure would be lost. Some have proposed the possibility of vacuum decay, a scenario in which our universe exists in a false vacuum state. If a bubble of true vacuum were to form and expand at the speed of light, it would obliterate everything in its path, fundamentally altering the laws of physics themselves. This possibility, although unsettling, could occur at any moment without warning, adding an element of unpredictability to the cosmos's fate. Each of these theories presents a vastly different picture of the universe's ultimate end. And while they seem distinct, they share a common thread: the continuing need for new ideas, new models, and new perspectives to better understand the universe in which we live. As we venture further into the unknown, the holographic principle and the theories that flow from it may offer the keys to answering some of the most profound questions ever posed about the cosmos. And in doing so, they might reveal not only the future of the universe, but the very nature of reality itself. However, in recent years, the viability of the Big Crunch theory has significantly diminished. In fact, observations of distant supernovae in the late 1990s revealed an astonishing discovery. The expansion of the universe is not slowing down, as the Big Crunch theory would require, but rather accelerating. This revelation sent shockwaves through the world of cosmology and redefined our understanding of the cosmos. What was once considered a straightforward conclusion, that gravity would eventually slow the expansion of the universe and lead to its eventual collapse, was now in question. The acceleration is attributed to a mysterious force known as dark energy, an enigmatic phenomenon that seems to counteract the gravitational pull of matter on a grand cosmic scale. The implications of this discovery were profound. Given our current understanding of dark energy and the continued observations of the universe's accelerating expansion, most cosmologists now consider the Big Crunch scenario increasingly unlikely. Instead, alternative theories such as the Big Freeze and the Big Rip have taken center stage, offering different visions for the universe's eventual fate. These theories, although still speculative, are seen as more probable outcomes for the distant future of our universe. Nevertheless, despite the mounting evidence against the Big Crunch, our understanding of dark energy remains limited. This is crucial because future discoveries, possibly revealing new properties of dark energy or even uncovering unknown forces, could alter our current perspective. It's not entirely out of the question that the Big Crunch could experience a revival of interest, or perhaps new concepts about the ultimate fate of the universe might emerge entirely. Thus, the journey of understanding the universe's end remains as much about the unknown as it does about the known. One such intriguing alternative is the concept of the Big Bounce, which offers a bold twist on the traditional idea of how our universe might end. The Big Bounce theory suggests that instead of a final, irreversible fate, the universe could experience cycles of expansion and contraction. This cyclical model imagines a universe that does not come to a definitive end, but instead goes through repeated phases of growth and collapse. According to this hypothesis, when our current phase of expansion eventually slows and reverses, the universe would begin to contract, pulling all matter and energy back together. The resulting collapse would lead to an incredibly hot and dense state, reminiscent of the conditions just before the Big Bang. However, the key difference between the Big Bounce and the Big Crunch lies in what happens at the moment of collapse. Rather than ending in a singularity where all matter is crushed into an infinitely small point, the contraction would reach a stage where quantum effects become significant, causing a bounce. This bounce would lead to the birth of a new phase of expansion, effectively restarting the cycle. The Big Bounce, therefore, presents a model of infinite cosmic cycles, where each cycle begins with a new Big Bang and ends in a new Big Crunch, only to start again. This theory attempts to solve some of the deep, unresolved questions about the origins and ultimate fate of the universe. In doing so, it offers a perspective in which the universe has no absolute beginning or end. But it's important to note that while the Big Bounce is an exciting possibility, it remains highly theoretical. Scientists continue to debate and explore various models of cosmic evolution, striving to find evidence that could either support or refute this concept. The true fate of our universe remains an elusive and profound mystery in cosmology. One of the more dramatic and unsettling scenarios that has emerged is the Big Rip, a concept that suggests an ultimate end where the universe will be torn apart at every level: matter, space, and even time itself. Central to this theory is the role of dark energy, the very same mysterious force responsible for the universe's accelerating expansion. In the Big Rip scenario, dark energy would not only continue to accelerate the expansion of the universe, but would gradually grow in strength, eventually overwhelming the fundamental forces that hold matter together. As the Big Rip approaches, galaxies would begin to tear apart, followed by solar systems, planets, and in the final moments, even atoms themselves would be ripped asunder. The fabric of space-time would unravel, bringing about an end to everything as we know it. This cataclysmic event would mark the ultimate conclusion of the universe, where nothing remains, not even the laws of physics as we understand them. However, while the Big Rip presents a chilling vision of the universe's end, current observations suggest that we are not on a path toward this extreme fate. The expansion of the universe, although accelerating, does not appear to be increasing at the rate required for a Big Rip to occur. Still, this scenario remains a fascinating possibility, a reminder of how much we still have to learn about dark energy and the long-term evolution of the cosmos. The shape and density of the universe are also crucial factors in determining its ultimate fate. Cosmologists have proposed three primary models for the structure of the universe: open, closed, and flat. Each of these models carries distinct implications for the future of the cosmos. An open universe, for example, is one where the density of matter is below a critical threshold. In this model, the universe would continue to expand forever. While the expansion might gradually slow down, it would never completely halt. Over time, galaxies would drift farther apart and the universe would grow colder and darker. In the distant future, even atoms could be torn apart in what would be known as the Big Rip. In contrast, a closed universe has a density above the critical threshold. In this model, the expansion would eventually slow down and reverse, with gravity overcoming the expansion and causing the universe to collapse in on itself, a big crunch. This scenario would lead to a state similar to the singularity of the Big Bang, where all matter and energy collapse into an infinitely small and dense point. The flat universe model, meanwhile, represents a delicate balance between the open and closed scenarios. Here, the expansion rate slows asymptotically, meaning it never quite reaches zero, but comes incredibly close. While the universe would continue to expand, the rate of that expansion would diminish over time. In this model, the universe would grow increasingly sparse and cold, but it would avoid both the catastrophic Big Rip and the Big Crunch. Recent observations strongly support the flat universe model, but the discovery of dark energy has complicated matters. While a flat universe was once seen as the most probable outcome, the accelerating expansion of the universe could alter that understanding. Dark energy's influence could result in a future where even a flat or closed universe expands forever, fundamentally shifting our entire perception of the universe's destiny. The idea of a cyclical universe, where the cosmos undergoes endless cycles of expansion and contraction, has long fascinated scientists and philosophers. This oscillating universe theory suggests that after each Big Bang, the universe expands, only to eventually slow down, reverse, and collapse into a Big Crunch. From the ashes of this collapse, another Big Bang would ignite the next cycle, continuing the cosmic dance. However, current evidence does not support this model. The discovery of dark energy, which accelerates the universe's expansion, poses a significant challenge to the idea of a contracting universe. Instead of slowing down, the expansion seems to be speeding up, making it increasingly unlikely that the universe will ever collapse. Furthermore, the concept of entropy, where disorder increases over time, suggests that if the universe were truly cyclical, each cycle would be longer and larger than the last. This would imply that we are currently in a cycle that is far larger and older than any previous one, a conclusion that contradicts our current understanding of the universe's age and development. Quantum fluctuations, the tiny variations in energy that occur at the smallest scales, might also play a crucial role in shaping the far future of the universe. As the universe continues to expand and cool over vast timescales, these fluctuations may become more pronounced. In an ever-expanding universe, matter and energy will become more diffuse, spread out across unimaginable distances. As this occurs, quantum fluctuations might trigger the spontaneous creation of particles, or even new structures in the void of space. Some theories suggest that these quantum fluctuations could give birth to new universes. Through a process called quantum tunneling, a small region of space might tunnel into a lower energy state, leading to the formation of a new cosmos, complete with its own set of physical laws and properties. In this way, the very fabric of space-time could give rise to entirely new realities. Quantum fluctuations could also influence the fate of black holes, those mysterious and massive objects that warp space and time. Over incomprehensibly long periods, black holes are thought to slowly evaporate through a process known as Hawking radiation. Quantum effects could play a role in determining the ultimate fate of black holes, including the information they release back into the universe as they evaporate. The fate of the universe will inevitably shape the future prospects for life and civilization. As the cosmos continues to evolve and expand, the environments in which life might emerge will also change. In a universe that keeps expanding indefinitely, civilizations might face growing challenges. Galaxies will drift farther apart, limiting access to resources and habitable planets. However, advanced civilizations could potentially adapt by harnessing the energy of stars or black holes, or even by developing interstellar travel technologies. If the universe were to end in a big crunch, life would be impossible in the final moments due to extreme densities and temperatures. Yet, long before that moment arrives, civilizations might thrive, perhaps even finding ways to escape to other universes or dimensions. The Big Freeze scenario, where the universe expands forever and grows increasingly cold and dark, presents its own unique challenges. As stars burn out and matter decays, sustaining life would become increasingly difficult. However, given the vast timescales involved, there might be enough time for life forms to evolve and adapt to the changing cosmic conditions, potentially finding ways to survive in a universe that grows ever colder. In the end, while the precise fate of the universe remains uncertain, these theories provide a window into the most profound questions of existence, whether through cyclical expansions and contractions, the tearing apart of space-time, or a gradual cooling and darkening of the cosmos. The ultimate fate of the universe is a mystery that continues to captivate scientists and dreamers alike.